Hello. Chetan, can you hear me?
Hello. Yeah, ma'am, you are audible, ma'am.
This sharing option is not enabled for me. Can you please enable it so that I can share my slides?
Sure, ma'am.
Ma'am, I have just made you the co-host so that you can share your screen now.
Okay. Thank you. Just thought of checking whether I am able to present or not. Later, I will just unshare it.
Sure, ma'am. Sure.
Hope it is visible to all of you.
Yes, ma'am, it's visible, ma'am.
Okay, thank you. Later, we'll go to slideshow mode. Till then, let this be like this.
Ma'am.
So, good evening, ma'am. This is Professor Chetan here, ma'am.
Good evening, sir.
Okay, I hope you remember me.
I think so. If I see you, I will definitely. It's long time, right?
Yes, ma'am. Yes, ma'am.
You're from CSA department, is
Yes,
it?
yes, exactly, ma'am.
Okay. Nice meeting all of you again. I don't know. We are back again
Yeah.
over here. Nice meeting all of you. Thank
Nice,
you.
ma'am. Okay, shall we start the session, ma'am?
Yeah, please.
Okay, so one of our faculty, Banupriya, assistant professor from Department of CSE, she's going to be, welcome you, ma'am.
Okay.
So afterwards, you can start the session, ma'am.
Sure. Thank you.
Okay. Hold to Banupriya, ma'am.
Hello, good evening, everyone. It gives me a great pleasure to welcome you all to this faculty development program. We are honored to have among us our distinguished the resource person, Dr. Nalini ma'am, and all our participants who have joined us from different institutions. I welcome you all, and I'm going to give some kind of introduction about our resource person, that is Dr. Nalini ma'am. Dr. Nalini ma'am, N. Nalini is a professor in CSE at Nitte Meenakshi Institute of Technology, Bangalore. She had received her MS from BITS Pilani in the year 1999 and PhD from Visvesvaraya Technological University in the year 2007. She has more than 26 years of teaching experience and along with the 19 years of research experience, she has numerous international journal and conference publications, book chapters and patents to her credit, and received Bharat Jyoti Award by India International Friendship Society in New Delhi in the year 2012 from Dr. Bhishma Narayan Singh, who is a former governor of Tamil Nadu and Assam. She had received Dr. Abdul Kalam Lifetime Achievement National Award for Excellence in Teaching and Research Publications and even the administration by International Institute for Social and Economic Reforms from IISER Bangalore in the year December 2014, 29th. So she is also the recipient of Distinguished Professor Award by Tech Next India in the year 2019 in association with Computer Society of India, CSI, Mumbai chapter, and Best Professor in Computer Science and Engineering Award by 26th Business School FIR Divang Mehta National Education Awards in regional round on 5th September 2018 at Bangalore. She is a lifetime member of ISTE, CSI, ACC, EEE, and IIFS, elected anonymously as Vice Chairman and Chairman Elect Computer Society of India Bangalore chapter for the years 2019 to 2021. Program Chair International Conference on Emerging Research in Cloud Computing, Information and Communication and Applications in ERCICA in the year 2013, 14, and 15, even 16, 18, 2020, 2022, 23, and RCICAM in the year 2024 and 2025 at NMIT Bangalore.
Madam, I think it's
So,
enough.
so there are, yeah, ma'am, it's a bit, I'm so happy that I'm being here with the, ma'am. So,
Thank you, ma'am. Thank you so
over
much.
to you, ma'am. Thank you,
Yeah,
ma'am.
thank you. So, yeah, first of all, my great thanks to Sri Devi Institute of Engineering and Technology, Tumkur, because I was there as a principal for short stint
Yes,
due
ma'am.
to unfortunate like family issues and etc. I have to move back to Nita Meenakshi. But I really, I mean, my stay of 4 months or 5 months at SIT was great, interacting with the great people like Hulinaikar sir, Patil sir, my colleagues over there, my student, PhD student Kiran sir, and all others, and Chetan sir also. Bhanupriya madam, I think we have not met, but
Yes, ma'am.
thank you so much for this introduction.
Thank you
And
so much, ma'am.
yeah, all the participants, it gives me an immense pleasure to present before you this quantum computing and algorithms. We all know that this is a new, like emerging kind of technology, because though people have started in the year 1994 or something like that, you all know that Bell Laboratories is a great place for inventions. Though we have not seen the place, but we have heard about the place, and great inventions happened from Stanford University, where with respect to computers, etc. You all know that internet is invented in Stanford University, and later the inventor moved to Bell Labs actually. So like this same thing happened with respect to quantum computing and algorithms also. Those who ever have devised the algorithms, Shor's algorithm or Grover's algorithm, and it's really surprising that Mr. Grover is an Indian, and we should be proud about Mr. Grover. His full name is Lav Kumar Grover. So he devised his algorithm at Stanford University. In his name, it has been kept. So such is the kind of research which is happening in the world level. And by the time you all know that it reaches to us, we will be understanding what is what. So, but with my little knowledge about this and my basic background of cryptography and network security, I will try to analyze how these quantum computing and algorithms are really beneficial to the world actually. In what way it is beneficial actually, we all talk about algorithms, right? So with respect to algorithms, what do we speak? We speak about order of complexity with respect to time and space. Those are the two main characteristics or the calculations we do whenever we talk about the algorithm. How one algorithm is better than the other algorithm is defined by this order of complexities only. If you have understood properly this order of complexities, then this quantum computing and algorithms with respect to quantum computing proposed by these many people like Shor's and Grovers and others make sense for us actually. So let us dive into this and let's see how best we can understand to a little extent, because to understand and to visualize this also requires a lot of insights, and with whatever we are trying to understand, let's see how best we can do that. So myself, Dr. Nalinian, working as professor at Nita Meenakshi Institute of Technology. Let me present my PPT in the slideshow mode. One second. Hope it is in the slideshow mode now. Can somebody confirm
Yes,
me?
ma'am. Yes, ma'am.
All right. So this is what I will be covering. So a lot information is there, but I will also be covering one of the examples so that we better understand how the things are different with respect to quantum computing. I will be explaining about Shor's algorithm with an example, why it makes sense for us. Okay. So with respect to this session overview and learning objectives, understand fundamental principles of quantum computing, and most of the resource persons yesterday, they've already spoken about this, but let me retouch upon that. Explore major quantum algorithms and their applications, analyze current state of quantum technology, that is NISQ era we call it as, because every computation will result in some noisy kind of a thing. Noise is nothing but the errors over here, okay? So noisy intermediate scale quantum, that is what is called as NISQ. We will understand a little extent of that, why it is so and why quantum computing is not so complete as of now, but people are working towards that, okay? So these are the examine real-world applications across industries. Detailed topics to be covered: introduction to quantum computing fundamentals, core quantum mechanical principles in computing, comparative analysis like quantum versus classical computing, Overview of major quantum algorithms categories. Let us deep dive into Shor's factorization algorithm. One example I will be explaining here. Then deep dive into Grover's search algorithm. I will just give the hint of that, how that search matters over here with respect to this algorithm. Okay. So quantum machine learning and AI applications, real world applications across industries, the current state, which I just spoke about, NISQ era and hardware limitations, that is noisy intermediate scale quantum. Then quantum error correction and fault tolerance, quantum supremacy, its advantage, then recent milestones, future prospects, challenges, research directions, conclusions, and key takeaways, and some discussions. So we all already heard about all these things in yesterday's sessions. Introduction to quantum computing. Definition and core concept. Quantum computing harnesses quantum mechanical phenomena. So, to understand quantum computing, we should know quantum mechanical phenomena, what it is actually, right? Such as superposition, entanglement, and interference to process information in fundamentally different ways than classical computers. What is the importance of these superposition, entanglement, etc. are how best we can store our information. That is a major concern over here. How fast we can process the information. So quantum computing is facilitating in those directions, the way we store the information, the way we process the information, how fast we are processing the information. That is been possible because of these kind of concepts. That is what the scientists have been harnessing, that how better we represent the information, right? All the time we represent in terms of zeros and ones only in classical computers, but with respect to quantum computers, so the representation itself is changing actually. Like we represent it in terms of qubits, already we know about that. Quantum bits, again, how that quantum bits are represented, what is the advantage of that, right? So can we represent so much in so little? That is the intention over here. So that's why we that's what has been called as qubits over here. And when you imagine thousands of gigabits of information compared to 1 kilobits of qubits, for example, which is easier to process, this qubits only, right? So that is what is making the sense with respect to calculation parts of processing parts of this quantum computing. So it represents a paradigm shift from binary classical bits, that is zeros and ones, to quantum bits, that is qubits, that can exist in multiple states simultaneously. So what is the meaning of this multiple states? Again, that superposition, entanglement, these things have been envisioned by the scientists, and they thought that is it not possible for us to represent these bits in terms of these quantum bits? That is how the existence of these quantum computing came into picture. So historical context and development. Theoretical foundations laid by Richard Feynman in 1982 and David Deutsch in 1985. This is not so old, because whenever we talk about cryptography, talk about Caesar cipher. Like Caesar is so many years, thousands of years before. But when it comes to quantum computing, it is a recent advancements like 1982 and onwards. So first quantum algorithms, Deutsch-Jozsa in 1992, Shor's algorithm 1994, and Grover's algorithm. These are the famous algorithms when we talk about quantum computing. So you can just see that in 1996, the algorithms have been evolved. So recent hardware advantages, IBM, Google, IonQ, and other quantum computing companies. So once people or the scientists or the researchers know that there is something over there, when these people propose these things like Shor's algorithms, Grover's algorithm, when they showed by example, maybe theoretically also, but then onwards, the quantum chips came into picture. IBM has developed quantum processors. So Google has developed its own processors. So then onwards, these algorithms have been run through, and they have found out that this is how it has been happening, and it is a correct kind of a thing. Okay. So that's how this quantum computing is gaining popularity. So revolutionary potential promises exponential speeds up for specific computational problems. So what is the meaning of this? Exponential speeds up. We want the algorithms to be, the problems to be solved in within fraction, not even fraction of a second, within that fractions of seconds. So because we all have heard about non-deterministic polynomial kind of algorithms, right? Still no solutions are existent for that. Some of the examples like traveling salesperson or N Queen's problem, like that we all have studied in our design and analysis of algorithms, right? So given a value of n can be anything, right? So can we find a solution for that? Still it is not. So theoretically it may be possible, but computationally it is not possible. So therefore there is a hope by using of these quantum computing computers, where we can reduce the order of complexity. That is the main intention why people work towards the algorithms. Better algorithms. Are we not satisfied with the divide and conquer techniques or branch and bone techniques? No, because so at some point of time, the system crashes. Whatever with computational processing speed is there, no, with respect to our laptops or servers, etc., they cannot go beyond certain point of time. So therefore, we need new algorithms, right? So people have thought differently how those kind of NP hard, NP complete kind of problems can be solved. So these are the various solutions, and that is how people have been succeeding towards that, because when they solve particular thing, new solution, new problems will emerge. Again, they will look into that. This is how the society of the world is, right? So therefore, scientists are they're curious to know how best particular problem can be solved. So one such example I will be explaining with respect to Shor's algorithm, why it is important. Okay, so this could revolutionize cryptography, because everything like security, when we talk about security is a major concern in the communication scenario, right? Be it in rest, be the data is in rest or be the data is in transit. So therefore, cryptographic solutions, available cryptographic solutions, can they sustain for long? So if we apply this quantum computing to break the ciphers, therefore cryptography is gone, right? So therefore, again, we need to have newer solutions or newer algorithms. Say, for example, RSA, that is Rivers-Shamir, Adelman, or elliptic curve cryptography. Those are the standard algorithms now. But when we look through this quantum computing, they are nothing actually, because within fraction of a second, they are breakable. The ciphers are breakable by these kind of computational techniques. Therefore, and we need to have more different kind of algorithms which are more secure, which are quantum computingly secure. That is the word which I'm trying to bring it over here. So therefore, these algorithms make sense because so far whatever algorithms we are having are not so secure in front of this quantum computing. So drug discovery, the drugs, the molecule, all those things in different ways, they will be joined and all those things. I'm not much into that, but what I understand is with respect to quantum computing, new revolutions can be brought in drug discovery. New drugs can be discovered. That is the advantage of quantum computing with respect to drug discovery. Similarly, in material science and optimization, they have the applications. So these algorithms have the potential to solve currently intractable problems in polynomial time. That's what I was trying to tell. Non-deterministic polynomial time algorithms, right? Polynomial time algorithms problems can be solved. But NP hard, that's what we call it as, right? NP hard, NP complete kind of problems are still existent. Mathematically, it is there, but computationally, it is not possible because existing computers cannot solve given particular value of n. So therefore, that is how the algorithms are, and that is how they have been categorized like that. And that is where this quantum computing comes into picture. So expected to create new fields of study and technological applications. So therefore, one second. Yeah, so these are fundamental quantum principles. Already we know that. Yeah. So superposition, the foundation of quantum advantage. Classical bit, we know that it is either 0 or 1 at any given time, but whereas quantum bit can exist in a linear combination of 0 and this is a representation which we do in quantum computing. We call it as a bracket, bracket. So KET, that's a representation we call for the zeros and ones, KET representation. states and mathematical representation. It is a complex notations, right? So absolute of alpha square and absolute of beta square is equal to 1. That is the expectation. So for example, 4-qubit system can represent all 16 possible binary combinations simultaneously. So just imagine 16 in the case of classical representation, we need to have all 16 possible binary combinations, right? 0, 0, 0, 0 to 1, 1, 1, 1. But in the case of a qubit system, only 4 qubits are enough to represent 16 possible binary combinations simultaneously. So therefore, that's a superposition which is helping us to do that. And that's how storing of 4 qubit is enough in compared to storing of all 16 possible binary combinations, right? So space is saved. And processing is as good as 16 possible binary combination. Therefore, order of complexity is also in terms of order of complexity, it is very, very good actually. So that is where this superposition technique is helping in quantum principles. Then entanglement, it's quantum correlation. 2 or more qubits become correlated such that measuring one instantly affects the other and creates non-local correlation that cannot be explained by classical physics. Einstein called it spooky action at a distance, because he also felt that this is something strange. Spooky in the sense it's a strange action. Essential for quantum algorithms and quantum communication protocols, interference, amplifying correct answers. So quantum amplitudes can interfere constructively or destructively. Both the things are possible here. Allows quantum algorithms to amplify correct answers and cancel incorrect ones. Core mechanism behind quantum computational speedups. This interference is another fundamental quantum principle. Then decoherence, the major challenge. Quantum states are extremely fragile and sensitive to environmental noise. That is where this NISQ is coming into picture. Noisy intermediate scale quantum. So interaction with environment causes quantum information to degrade rapidly. Coherence times typically microseconds to milliseconds, major engine challenge requiring sophisticated algorithms. So there's a detailed analysis of quantum versus classical computing. With respect to information storage and representation, classical is 0 or 1 with deterministic states. It can be either 0 or 1. With respect to quantum, information stored in qubits, allowing superposition of 0 and 1. So coin is a best example. So everybody speaks about coin when we talk about quantum computing. Coin has both head and tail, but in between that circumference is also there, right? So that is a superposition of both head and tail. So therefore, this is how qubits is interpreted here. So classical n bit represent 1 of 2 to the power of n possible states. That's what happens in classical, right? With respect to our computations. Quantum n qubits can represent 2 to the power of n complex amplitudes simultaneously. So this is the difference between those two things. 2 to the power of n possible states, whereas here 2 to the power of n complex amplitudes simultaneously. That we have seen that absolute of alpha square plus absolute of beta square is equal to 1, right? So that is how quantum, with respect to quantum, this is happening. So processing capabilities, classical sequential processing through logic gates, quantum parallel processing through quantum operations on superposed states. That representation also sir explained yesterday. So classical deterministic or probabilistic algorithms, but when it comes to quantum, probabilistic algorithms with interference effects. Therefore, knowledge of probability is very, very much required when we talk about this quantum computing. So performance characteristics, error rates, quantum is 10 to the power of minus 3, then operating temperature. These things matter a lot actually, because quantum near absolute zero temperature is required, because when the things get heated up, the loss of information happens. So therefore, it has to be maintained. Environment should be very, very friendly. That is what they're trying to tell over here. Then scalability, classical billions of transistors, just compared to quantum, just see hundreds of qubits. That is more than enough, which replaces billions of transistors. So key quantum advantages, exponential speed up for integer factorization. So this is about Shor's algorithm. This is the one which he proposed actually. Integer factorization plays very, very vital role with respect to cryptography. So where we talk about RSA, the security or the strength of RSA lies in not doing the integer factorization. Factorization is not possible in RSA algorithm, but Shor's algorithm has proved that within some time the integer factorization is possible. So that is where security of the cryptographic algorithms is at stake. So that is how, because if the cryptographic algorithms are broken, so far we have been thinking that RSA is very strong, or elliptic curve cryptography is very strong algorithm. But because of these computational complexities or power of these quantum computing, I mean, we can tell that RSA and elliptic curve cryptography are not so secure as of now. So that is what he's trying to show. But as of now, a lot of other complexities are required. So therefore, he's sticking on to this integer factorization. Factoring that n value in RSA is very, very important to break it. But so far, it is not possible to break the integer do the integer factorization, that is NP complete problem as on today. So that is where we are talking about this quantum and classical computing. Then I think this slide has to go down only, then I can read this slide. Yeah. Quadratic speedup for unstructured search. This is Grover's algorithm. He's an Indian we should be proud of, and he proposed this searching in the unstructured search. So we all know that linear search, binary search, or all those things are there, right? In the unstructured environment, how best we can search a particular item, right? So this is applicable to cryptographic algorithms also. If one succeeds in searching the particular key which is used out of pools of keys, then cipher is broken, right? So again, this is where this Grover's algorithms also playing a vital role. The natural simulation of quantum systems in chemistry, materials, and enhanced machine learning and optimization capabilities. Everywhere the possibility of quantum computing is happening. So classification of quantum algorithms by problem domain, algebraic and number theoretic algorithms. So this is where Shor's algorithm is proposed, like integer factorization with exponential speed up. Exponential speed up in the sense, with that speed, integer factorization is happening. So breaks RSA encryption, threat to current cryptographic systems. That's what I was trying to explain. RSA is no longer secure. ECC is no longer secure because of these kind of quantum algorithms. So if you see the complexity in classical, it is order of exponentiation of logarithm of n to the power of 1/3 versus quantum order of log n to log n whole cube. So therefore, it is exponentially, it is speed is happening with respect to that. So the RSA is breakable, breakable within a certain possible time. So far, they think that if it is 2048 is the size of the key which is used, it will take hundreds of years to break that. But no longer it is like that now because of these quantum algorithms. So quantum Fourier transform, efficient frequency domain analysis, hidden subgroup problem, generalizes many quantum algorithms, then search and optimization algorithms. So this is where Grover's algorithm comes into picture. It is exclusively working on unstructured database. We all have seen structured database, right? Relational database is a structured database because everything we write it in terms of rows and columns. Or in the CSV files, comma separated value. It is a structured database, right? So, but Grover's algorithm is possible to be applied on unstructured database, and within certain time, it will find out the what is being searched for. So search with quadratic speed up, you can see here. So complexity of classical is order of n. That's a worst case order of complexity. Whereas in the quantum, it is order of square root of n. So just imagine if order of n is 100, quantum is only 10. So square root of 100 is 10, right? So such is the reduction in the speed. So therefore, even cryptographic key search is very, very easy when quantum algorithms are used. So that is where the threat is actually, because of computational speed up of these kind of algorithms, security algorithms are a threat. So just imagine, because there's a need for improvised algorithms or more secure algorithms. This is where exactly it is fitting into for our in cryptography. Other areas, as I mentioned, materials and chemistry, those drug discovery, etc. People who are expert in those domains, they can talk about that. So as far as my knowledge, since I know these cryptographic algorithms, I'm trying to bring in these algorithms with respect to cryptography. So amplitude amplification, generalization of Grover's search technique, quantum walk algorithms, enhance graph traversal and search, right? Graph traversal is again like searching only. It is applicable in communication protocols. So the best route or the worst route, all those things we search it for, right? Because our packets has to reach to the destination within certain specified time. So therefore, when we do this kind of quantum algorithms, searching that traversing becomes very, very easy actually. So graph traversal techniques also we already studied, breadth first search, all those things, right? So therefore, when we apply that to communication protocols, that makes sense for us. And a lot more information or examples and some algorithms written in particular code is given in this website, quantuminspire.com, K-base, Grover algorithm is search. So you can look into that. They've already written some coding techniques over there. If you are interested, you can go through that. So as I mentioned, I wanted to tell you about the Shor's algorithm. What is the necessity, or why did he propose this, right? We all know that scientists work towards so many complex algorithms or complex problem domains, finding new solution. That is their intention actually. So Shor's algorithm is a quantum algorithm designed to find a prime factors. So this is very, very important. It's a prime number factorization, okay? Prime number or integer is a prime is also an integer. So integer factorization of an integer. It leverages quantum mechanics to efficiently solve a problem that is computationally difficult. Computationally difficult for classical computers. Where classical computers fails, quantum computers are helping us. So this is an example of how it works to factorize a number. For the example's sake, we take smaller numbers so that we can understand it. But this is not the case. We should be exploring it for larger prime numbers. Large prime numbers, whether those prime numbers can be factored or not. We all know that factorization of number is very, very difficult when we talk about RSA. That is where the strength of RSA lies in. So therefore, prime factorization is one of the NP-hard problem. So for given a value of very large integer prime number, factorization is not being able to be done so far. So that is what is the problem. But quantum algorithms to a certain extent have enhanced the capability of factorization. Therefore, cryptographic algorithms are not so secure now. So let me explain this. Say n is equal to 15. We all know that it is an integer. So we need to get the prime factors for this. Choose a random. This is the classical steps. But where this Shor's algorithms or quantum computing fits in, I will tell it in the next slide. So these are the classical steps. Choose a random number. That is, pick a random integer a such that 1 is less than a is less than n. What is n over here? N is equal to 15. That is an example which has been proposed by Shor only. So everybody is using that. So 1 is less than a is less than n, and GCD of this a. So this is what we have chosen, right? In a random integer a. So the GCD of this a and this number n, which is equal to 15, is equal to 1. So this is how all this RSA elliptical cryptography works, based on these kind of principles only. So for n is equal to 15, let's choose a is equal to 7. You can work through in the computer, that will give an answer. So you can choose a is equal to 7. So what is the condition? GCD of 7 and 15 should be 1. So when we find out GCD of 7 and 15, it is to be 1. So this is a valid choice. So that was the condition, right? Pick a random integer a such that this holds good, and GCD also holds good for 1. So accordingly, A is equal to 7 and GCD, and we know that 7 is less than n, 1 is less than 7 is less than n. That's how it has been chosen, right? So this is a valid choice. So now we have chosen A, and capital N is equal to 15 we are having. Next thing is we need to find the order, which is also called as a period of A modulo n of R, okay? 1 second, yeah. So this is the smallest positive integer r, such that this is a condition. A to the power of r is congruential to 1 mod n. So what is the meaning of congruential? Whenever you divide this by n, the remainder should be 1. Okay. So a to the power of r is mod n is equal to 1 mod n. So that is the meaning of congruential. So therefore, remainder should be 1. That is the intention here. So this step is where quantum computer provides a significant advantage. So as of now, this is a small number, right? So therefore, we can easily calculate this order or period. So we start from 1. So this R, we start from 1, 2, 3, 4, like that we go on, such that which number of R gives us the 1 over here, we stop it at that point of time. Say, for example, we have chosen A is equal to 7 in the first step, n is equal to 15 given. What we want to find the prime factors of this number. So we start with 1, 7 to the power of 1, a is equal to 7, r is equal to 1. We start with this. So we know that 7 to the power of 1 is 1 and 7 mod 15 is 7, right? So the remainder is 7. So that is 7 to the power of 1 is congruential to 7 mod 15. So next we increase this. We calculate, go on doing this from starting from 1 till where we need to find particular number which gives us this 1 over here. Hope you're all getting this. Remainder to be 1. So 7 to the power square is 49. 49 mod 15, right? 3 times it goes. Remainder is 4. So therefore, it is congruential to 4 mod 15. 7 to the power of 3, like that, it is 13 mod 15. 7 to the power of 4, luckily we got it to be 1 over here. It can be anything, like 7 to the power of 5, 6, and go on trying to do that one. So that is where, that is the intention, right? This is the smallest positive integer r, such that a to the power of is congruential to 1 mod n. So what is that? This is the order or period of a modulo n. So therefore, we got that number. So therefore, r is equal to 4. This is the order. So this order calculation is there, no? That is where this Shor's finding is helping. So they have a different mechanism. The one which we did, it's very simple, very classical. That's how we did that. Classical computers do it like that. But when it comes to quantum computers, there's a period finding. What was the period over there? R is equal to 4, right? This is the smallest example, but you need to imagine bigger numbers. So this is the core of the Shor's algorithm, where a quantum computer efficiently finds the period R within less number of time, less possible time. This order of complexity is very, very less, finding that R. So this is where quantum subroutine helps. So what did he do? Like prepare a superposition, create a superposition of states in an input register representing all possible exponents, apply modular exponentiation, implement the function f of x is equal to a to the power of x mod n using quantum gates. This creates a superposition of this x a to the power of x mod n states. Then he performed quantum Fourier transform QFT, apply a QFT to the input register. This transforms the periodic pattern in the superposition into peaks at frequencies related to the period R. So that means we imagine, right, 16 different possibilities represent 4 qubits only. This is what is happening here. So measure the input register. Measuring the input register is a value related to k by r, where k is an integer. Use continued fractions, classically process the measured value to find a fraction k by r and thus determine r. So this is the process which has been applied by Shor to get that period r. What we got in classical, that r is equal to 4. Well, how to imagine it's a bigger numbers. This is an example, say smaller numbers are taken. So this is the process which is applied to determine that r. This is where quantum subroutine works for that. So classical steps continue again, only for that R quantum is applied. So again, classical steps are continued. You imagine, right? Classical steps first, then quantum steps, then classical steps to get the solution. So check the order R. If R is odd, these are the conditions again. Or if a to the power of R by 2 is congruential to -1 mod n, restart the process with a new random A. We started with A is equal to 7, right? So you need to check this. So if R is odd, luckily we got R is equal to 4. So it is not odd. If it would have been odd and this congruential value, the remainder is supposed to be -1, then again you need to restart the process with a new random R because of its own problems. So in our example, R is equal to 4, which is even, and 7 to the power of 4 by 2 is equal to 7 square, which is 49, is congruential to 4 mod 15, which is not -1 mod 15, right? So therefore we are safe. So we proceed. So this is the step to be checked. So this is the checking procedure over here. Check the order R. What was R? R is equal to 4. So it is even and it is not like -1 mod n. So therefore we proceed. So how to calculate the factors? Again, this is a classical step only. Compute GCD of a to the power of r by 2 -1 comma n and GCD of a to the power of r by 2 plus 1 comma n. These will be the prime factors of n. Just imagine mathematically they have correlated all these things and they have succeeded in getting the prime numbers, prime factors of the integer that is 15. So now A we knew, that is GCD of 7 to the power of 4 by 2, R was 4 by 2 -1 comma 15, which is equal to, when we calculate that, it is nothing but GCD of 48 comma 15, which is 3. So these two are the numbers, like first one and the second one are the factors, prime factors of n. So the formula is already there. So GCD of second one, which is equal to GCD of 50 comma 15, which is equal to 5. So therefore, we have succeeded in getting the prime factors of the integer 15, which is 3 into 5 is nothing but 15. So therefore, the factors of 15 are 3 and 5. We all know that, but it is simple, right? But when we apply quantum computing for larger numbers, larger integers, we should not be sticking ourselves to this 15. This is a very, very small number. Just to understand how quantum computing works, we have taken this example, but you need to visualize 2048 bits of representations of the integers, and getting the prime factors for that is very, very difficult using the classical computers, where they have failed. Those algorithms have failed, but quantum algorithms have passed. So this explains the Shor's algorithm. Again, Shor's algorithm, where did we apply this quantum computing? With respect to finding that R. So it's quantum subroutine. So classical state, quantum subroutine state. Again, we came back to checking the order, which is a classical step. Finally, calculating the factor, which is also a classical step. So therefore, in between, we embedded that quantum computing concept such that we were able to determine the factors of the integer. Hope this is fine. Any doubts so far? So what we are trying to do here, I'm sure all of us are getting to know. So quantum concepts have been applied in between to get a solution within possible speed. So that speed is very, very important. Exponential speed, the results are being got. So that's where the advantages of these kind of algorithms. Hope I was able to explain what is the importance of that Shor's algorithm. So similar to that, a lot of other algorithms are coming into picture. People have started working towards various possibilities, optimization algorithms, like simulation and physical system algorithms, variational quantum eigensolver, finding ground states of molecules. Just imagine, people have been working towards these things. Quantum approximate optimization algorithm, combinatorial optimization, because this combinatorics is another very, very important phase, like in the mathematics. So where optimal solutions are not existent, again, quantum computing is helping in those things. Quantum phase estimation, measuring eigenvalues of unitary operators. So these are the mathematically solvable, theoretically solvable, but computationally non-solvable so far. But quantum computing is helping to solve these kind of problems. Then Trotter-Suzuki decomposition, simulating time evolution of quantum systems. Then machine learning and AI algorithms also, why this should be left behind, right? So therefore, application of quantum on this machine learning AI algorithms is a feasibility. Quantum support vector machines. We already heard about support vector machine, SVMs in AI and ML, right? But when we apply quantum to that, so what it happens? Enhanced pattern classification. That is the intention, right? Better the solution with respect to quality, with respect to space, with respect to speed. That is what we talk about when we talk about the algorithms. So that is what is happening. Enhanced pattern classification, quantum principal component analysis, PCA, what we call it as dimensionality reduction algorithm. PCA is a dimensionality reduction algorithm. We all have applied in machine learning algorithms, right? So if there are thousands of parameters, if we apply principal component analysis, it will only choose what is required, right? Dimensionality reduction. So therefore, when we apply quantum to that, again, much more valid dimensionality reduction happens. Then quantum neural networks, brain-inspired quantum computing models, HHL algorithms solving linear systems of equations exponentially faster. These are the higher advanced algorithms people are working by combining quantum advantages. So again, I just dealt with this. Shor's algorithm, quantum factorization, developed by Peter Shor at Bell Labs. I was mentioning, right? All inventions are happening in Bell Labs, which is, and people are from Stanford universities, and solves integer factorization problem exponentially faster than the best known classical algorithm. This is the intention. Why we talk about algorithms is either with respect to time complexity and space complexity. So therefore, exponentially faster if you achieve, then you are solving those kind of problems. Poses existential threat to RS and ECC and other public key cryptographic system. We have been thinking that RS and ECC are more secure as on today, but because of quantum factorization, they are no longer secure. That's why the threat is to those kind of algorithms. Motivated massive investment in quantum computing research and post-quantum cryptography. Then mathematical foundation and complexity, given a composite integer and find its prime factors. I just explained all those things to all of you. Then algorithm steps in detail, classical pre-processing with an example. I already explained it. Let me move to the next one. Grover's algorithm. So this is a quantum search deep dive, like unstructured environment searching, right? Algorithm overview and problem statement developed by Love Kumar Grover at Bell Labs. Again, just imagine things are happening in Bell Labs only in 1996. Solves unstructured search problem with quadratic speed up. That was exponential speed up with respect to Shor. Here it is quadratic speed up. There's difference again. By what amount the speed up is happening, based on that they determine whether it is exponential or whether it is quadratic. So problem, find marked item in unsorted database of n items. Oracle-based algorithm requiring black box access to search function. So complexity analysis, classical linear search, we all know that our best order of complexity is order of 1. Otherwise, we'll have to search the entire search, right? Linear search. So if there are n elements have to be searched. So therefore, order of n, queries on average, O to the power of n worst case, and best case is order of 1. Grover's quantum search, it is order of square root of n. Just imagine if order of n was 100, order of square root of n is square root of 100 is 10, right? So therefore, by that amount, it has been reduced. Queries with high success probability. So optimal quantum search algorithm proven by Bennett et al. Success probability is approximated to 1 after pi square root of n by 4 iterations. This is how the calculations are done with respect to algorithmic steps, okay? So algorithm mechanics, step-by-step initiation, create uniform superpositions over all n states, Oracle application. This is the steps, Oracle application. Again, it has its own applicability. Apply Oracle function, which is if X is marked and otherwise. Diffusion operator, apply inversion about average amplitude, iteration, repeat Oracle plus diffusion approximately these many number of times. Measurement, measure final state to obtain marked item with high probability. So this is a different level of applications of these steps over here. One should be very, very thorough in applying these kind of intermediate steps like Oracle application, diffusion operator, iteration, and measurement. And Python is also having its own packages. Some of them are really working. May not be for all types of possibilities, but to a certain extent, it has been succeeding. And people have been working towards that again. So geometric interpretation algorithm operates in a 2D subspace spanned by marked and unmarked states. Each iteration rotates state vector by fixed angle toward marked subspace. It's a superposition, right? So rotation angle 2 by square root of n for large n. So applications and extensions, database search. This Grover algorithm is basically for unstructured search algorithm. And pattern matching. This also a searching algorithm only, right? Search through all the patterns and whichever matches, right? That's the pattern matching in unsorted data. It is applicable in cryptanalysis. How it is applicable? Searching for encryption keys. Again, large pool of keys. In that, you'll be searching particular key. So searching for encryption keys, solving NP-complete problems with quadratic speedup, amplitude amplification, generalization to multiple marked items, quantum machine learning, speeding up various machine learning algorithms. So paradigms and approaches. Quantum enhanced classical machine learning, use quantum computers to accelerate classical machine algorithms. Already we have seen SVMs, the PCA, all those things, right? So accelerate classical ML algorithms. Acceleration with respect to speed only, right? Finding a solution within a shortest span of time. What it was taking in classical algorithms, it should be reduced by quadratic amount or exponential amount. So quantum speedups for linear algebra operations like matrix multiplication, SVD, etc. Examples, quantum principal component analysis, PCA I mentioned, quantum support vector machines I mentioned, HHL algorithm for solving linear systems, exponential speedup under specific conditions. Then quantum neural networks and deep learning, parameterized quantum circuits as quantum neural networks, variational quantum classifiers using gradient-based optimization. All these things are the statements in neural networks and deep learning. Hope most of you already work towards these kind of things. Gradient-based optimization techniques, ADA boost, so many things are there, right? So therefore, you can relate it to them and apply it with respect to quantum. Then quantum convolutional neural network for image processing, hybrid classical quantum neural architectures, hybridization between classical as well as quantum. So these things are also people are writing the papers and working towards that. Variational quantum algorithms for machine learning, quantum approximate optimization algorithm, QA/OA for combinatorial ML problems. Then variational quantum eigensolver, that is VQE, to find optimal solutions, quantum variational autoencoders for data compression. Autoencoders also you might have already studied in machine learning algorithms. So apply the flavors of this quantum computing or enhance the possibilities of those kind of algorithms. Accelerate, that is the best word, accelerate those algorithms. Theoretical advantages, exponential state space. N qubits represent 2 to the power n dimensional Hilbert space. Again, Hilbert space with what is the meaning of this state space is, say for example, if n is equal to 4, right? So how many values it can hold? 2 to the power of 4, which is 16. So that is a state space for us. So therefore, how do we represent that state space using the qubits is a thing over here. So 2 to the power of n dimensional Hilbert space is again a mechanism with respect to this qubits. Then quantum feature maps, nonlinear mappings to high dimensional feature spaces. Feature maps, again, all the things what you studied in classical algorithms with respect to machine learning, neural networks, etc., you can relate it to this quantum. So they're just juxtaposed with quantum word over here, quantum feature maps. What is the advantage of quantum? It reduces the dimensionality. Reductions is possible. A reduction in time, processing time is the main thing over here, because representation itself is reduced, right? The data representation. Instead of 16 different possibilities, you're only four qubits are representing the same space. So that is where the advantage, right? So therefore, everywhere you can apply, wherever your processing speed is there and wherever space is there, you can apply this quantum and work towards that. Quantum entanglement, capturing complex correlations in data is possibility. Then current limitation and NISQ error challenges, as I mentioned, so far it is not devoid of errors, that is noise. So therefore, that also has to be worked out. Limited qubit counts and higher error rates in current devices. Quantum memory, QRAM, not yet practically available, though people are doing these chips, all those things, but still not full-fledged. Just like the way we have our laptops, or already we are having GPU-based processors, these quantum-based processors still are in the process. So it's not full-fledged, but solutions are available, right? So we are already spoken about so many algorithms. We need to bring into this chip kind of a thing. So classical simulation often competitive for small problem sizes. Need for quantum classical hybrid approaches. So up to certain extent, we have seen in Shor's algorithms only, right? Up to certain extent, we have done classical approach. In between, he introduced a quantum approach. Again, we came back to classical approach. That's a hybridized approach. So like that, it has to be done. Then coming to this real world applications across industries, cryptography and cybersecurity, majorly breaking current encryption. Shor's algorithm threatens RSA, ECC, and Diffie-Hellman key exchange. If quantum is applied over that, all these algorithms so far, whatever they're claiming to be the best and superior unbreakable algorithms, is possible to be broken by this quantum computing technologies. So quantum key distribution. So unconditionally secure communication. Then post-quantum cryptography, developing quantum resistant cryptographic methods. What's the meaning of quantum resistant cryptographic methods? RSA, ECC, DH key exchange are not quantum resistant. If you apply quantum, they are breakable, right? So therefore, if you apply quantum mechanisms also, that should not be breakable. That is the intention. Therefore, quantum resistant encryption methods to be evolved. So therefore, quantum random number generation for enhanced security. So far, random number generators, they're all related to cryptography only. Random number generators, again, there are so many properties. Which one can be considered as random numbers, which can be used cryptographically secure random numbers, we call it as Blum-Blum-Shub generator is the one which has been used in cryptography, where whatever the random number is generated, no, that will be taken as a keys, and those keys are meant to be secure.
Excuse me, ma'am. Sorry
Yes,
for
yes.
interrupting, ma'am.
Yeah.
Actually, can you be little slower,
Faster?
ma'am?
Slower
ma'am,
or
you are
faster?
little slow is needed, ma'am. That's why.
Slower. Okay, fine.
Okay.
All
Thank you,
right.
ma'am. Sorry.
No, it's okay. I thought, all right.
Thank you.
So I was talking about this cryptography, right? So if you all are well versed with cryptography and cybersecurity technologies, these are the algorithms: RSA, ECC, elliptic cryptography, Diffie-Hellman key exchange. We all would have studied that one. But when we look into aspects of perspectives of quantum, they are no longer secure now. So because we already seen that this integer factorization is possible using Shor's algorithm within fraction of a second. I mean, whatever we quoted to be unbreakable, it is possible to break because of these kind of algorithms. So that is where these quantum algorithms are playing the game kind of a thing, I can tell, right? So because they are existent now, there is a threat to this kind of algorithm. Therefore, to make them to be more secure, we again have to apply quantum to that. So therefore, quantum resistant encryption methods has to be developed. So that is the intention. RSA is not quantum resistant. ECC is not quantum resistant. DH key, that is Diffie-Hellman key exchange algorithm, is not quantum resistant. As of now, we feel that nobody can break them. But by the invention of this quantum computing technology, they are no longer secure. So therefore, we need to evolve or develop more secure algorithms which are quantum resistant. When do we say they are quantum resistant? Given this time period also, applying quantum algorithms also, they should not be able to find out those factors. We found out those factors, right? 3 into 5. That is the factors, prime factors of that integer 15. This is a small example. You should visualize bigger integers, which are there in RS and ECC. So therefore, applying this quantum also, it should be unbreakable. We should not find that 3 and 5. Then only we say that it is quantum resistant. Hope that is fine, right? So quantum random number generator for enhanced security. Again, random numbers are the ones which play a vital role in cryptographic algorithms. We say that cryptographically secure random numbers. And again, it's a wide field. Actually, if you are interested, which random number generated by which algorithm are more secure to be used in these kind of algorithms. Again, it's a different study area. So if you are interested, you can look through that. Because I'm a bit well versed with these cryptographic algorithms, I'm trying to explain more about that. Coming to this drug discovery and healthcare, people who are working with respect to drug discovery and healthcare, they can look more into that. Molecular simulation, like modeling complex biological molecules and drug interactions. Because in the laboratory, people who work towards this drug discovery, they can play around with this kind of superposition, interference, all those things are there. No, they can evolve more different kinds of drugs actually, and their benefits also can be explored. So that's what I understood from this. Then protein folding prediction, understanding 3D structure from amino acid sequences. Those are in this drug discovery domain. They know all these things. With my little understanding, I'm trying to tell that it's a molecular structure, right? So therefore, every drug, every chemical which has been used, it will have its own properties. When I combine all these things, and with respect to quantum, again, you can develop new drugs which is more beneficial to the human mankind, right? So that is what they're trying to tell over here. Then drug target interaction analysis, accelerating pharmaceutical search, then personalized medicine, optimizing treatment plans based on individual genetics. Just imagine every person's genetics is different. My genes are different from other person's genes, right? A particular gene, if it is affected in a particular individual, how better the treatment can be done. So all those things are possible when they talk about this quantum, because all possibilities are explored which are limited in the classical approach. So that is where this quantum computing is playing a major role. And I think this is going to change the way people are dealt with respect to their health. So medical imaging, enhanced MRI and quantum sensing for diagnostics. We all know MRI scanning, all those things we are doing it, right? Again, it is limited to 2D kind of a thing. Again, we can visualize with respect to 3D kind of a thing, which is human body is a 3D representation in the world. So therefore, like that also it is possible, it seems. So that's what I have tried to understand. Then coming to another domain, in financial services and economics, portfolio optimization, finding optimal asset allocation strategies. Asset allocations like portfolio optimization. But say, for example, you have some amount in your bank, right? So optimal asset allocation strategies also it will give. You invest in FD, you invest in land, you invest in some other SIPs, systematic investment plans. So it will give us optimal asset allocation strategies when we work with respect to, with the help of this quantum computing. Then risk analysis, Monte Carlo simulations for complex financial instruments. So Monte Carlo plays a very, very important role in probability and simulation algorithms. And it will predict based on the previous step what is going to happen in the next. So these Monte Carlo simulations are very, very famous. So one can do these kind of analysis, risk analysis in the market, systematic plans in marketing strategies or investment strategies. There will always be a risk, right? So I think that's how I've understood it. So correct me if I'm wrong. Those are into financial services, they know much. Those are into economics, they know much about these Monte Carlo simulations. Then fraud detection, pattern recognition in transaction data, high frequency trading, faster algorithmic trading strategies. So enhancement in the trading strategies it is going to give you. Nowadays, recommendations are there, right? Recommender algorithms, machine learning recommendations it will give. If we invest this much in this, for example, industries, what is the after a certain point of time, which is going to boom. So whether you have to sell or not to sell, keep it to yourself, or better to sell, or wait for some more time, all this is the recommendations. So therefore, these algorithms will be much more advanced with respect to current existing machine learning algorithms. We all know machine learning learns by training, learns by knowledge, like that. We train the model and accordingly it will tell everything. This quantum computing is way beyond that. It does in a very faster way. That is the intention over here. What has been happening, say it takes 100 hours, quantum computing takes 10 hours. What is the reduction here, right? So that is the thing which people are looking for. Credit scoring, enhanced machine learning models. Again, credit scoring with respect to financial services and economics. You all know about CIBIL scoring, all those things, right? Similar to that, credit scoring is also there, which determines the individual's capabilities with respect to finance. So other possibilities are material science and chemistry. I'm not much into that. I don't know about this. Those are working in these areas. They can look into that. Then logistics and supply chain optimization. Again, route optimization. Logistics is, we all know that, right? Courier services, logistics services, etc. supply chain optimization, supply demand chain, demand supply chain, right? So optimization, again, route optimization, solving traveling salesman and vehicle routing problems, supply chain management, optimizing inventory and distribution networks, traffic flow optimization, managing urban transportation systems like Bangalore, if you imagine how chaotic, right, the traffic. So how best it can be optimized by giving all the inputs, possibilities. So quantum will help in solving the problems in lesser amount of time, very, very lesser amount of time, exponential time reduction or quadratic time reduction. So that is how it has been helpful. Then resource allocation, optimizing scarce resources across multiple constraints. So there and all, wherever people felt that no solution is existent, quantum computing is helping to give the solutions. That is where the approach is. Then the current state, of course, quantum is still not final one. It takes people to develop perfect machines, right? So far, these are the problems existent. NISQ error definition and characteristics. NISQ stands for noisy intermediate scale quantum. So what is the meaning of that? Intermediate scale, it is ranging from 50 to 1000 qubits beyond classical simulation. That means this is the noisy scale actually. So therefore, everything is not perfect. Noisy is there, that is high error rates, no full quantum error correction, because in the classical computing environment, we already have error correction detection mechanisms, right? So, but in the case of quantum, still it is not there, still the scale is high. Algorithms are required again, quantum algorithms are required to reduce those noises, limited coherence times and gate fidelities. Then current quantum hardware landscape, IBM has developed 1000+ qubit system, Condor, Flamingo with superconducting technology. Then Google 7 qubits Sycamore processor claims quantum supremacy. Then IonQ 64 qubits using trapped ion technology, high fidelity gates. Then atom computing 1180 neutral atom qubits record breaking system. And Quantinum 56 qubits with trapped ions focus on quantum volume. So already these organizations, these companies have developed this quantum hardware using these technologies, ion technology mainly. I mean, those are into semiconductor and this kind of processor development. They know the meaning of this. But as a computer teacher or a professor over here, we all know that how the processors are built, chip technology, etc., etc. So the same way, these quantum chips are also being developed by these organizations. Of course, what is the intention? The reduction in the time, exponentially or quadrilaterally. So that is more important. That is where they're trying to contribute. Then NISQ era algorithms and applications, variational quantum eigensolver, near-term quantum chemistry. These are all very high level of algorithms. One should be very, very thorough with probability and statistics, probability majorly, eigenvectors, solvers, all these things are the, with respect to mathematics, where mathematics and you all know that physics, mathematics and computers, these three things are put together in quantum, right? So one should have a thorough knowledge of all these things to understand all these things. So quantum approximate optimization algorithms, then quantum machine learning models. So machine learning models, we all know, a lot of machine learning models are there. When you apply quantum flavor to that, so therefore there's a speedness is increased exponential or quadrilaterally. So pattern recognition becomes very easy. That's what unstructured searching, right? That's what they're trying to tell here. Yeah, it's not linear. Everything you're not putting it in ascending order or binary search. It is not like that. So it is scattered. The search space, in the search space, everything is scattered. It is not organized. That is why we call it as unstructured. Given that scenario also, so quantum algorithms are able to detect particular item which we are trying to search within these exponential times. That is what the success factor of these quantum algorithms are. So error mitigation techniques, improving results without full error correction. So like mitigation techniques, errors. Every communication or transactions will have errors, right? So how the error detection algorithms are already exist, and error detection and correction. If you have studied computer networks, we all know about that. If there is a error is happening, also error correction techniques are there. It will correct those errors, and correct information is communicated across to the destination. So that is where these kind of things are also playing important roles. Then key limitations: cannot run Shor's algorithms for cryptographically relevant problem sizes. Classical computers often remain competitive for practical problems, limited circuit depth due to decoherence and gate errors. As I mentioned, everything is not perfect so far with respect to quantum computers. So maybe some people have told that we have been successful, but to a certain extent only, right? So path forward, focus on problems where quantum advantage is achievable with NISQ devices. Then development of better error mitigation and correction techniques, building larger and more stable quantum systems. So like that, lot of challenges are there. Some of them are here. I think I will just skip that. Recent progress and breakthroughs. Google in 2023 demonstrated below threshold error correction with surface codes. So only those who know it. So therefore, it's all already been happening. For an end user, it is as good as like we are using the laptop or the desktop. That's it. If you are given a quantum computer in front of you, we will all be just be using it like that. Already behind the screen, these quantum algorithms would be running. So IBM advancing logical qubit implementations and error syndrome detection. Error rates improving, like it is improving. So these are the recent breakthroughs. The threshold theorem, you just name it. People have been working like anything to solve the problems. Requires thousands of physical qubits per logical qubit. Part 2, fault tolerant universal quantum computing. Fault tolerant machines again. So no fault should happen, right? That is the thing. Fault tolerant algorithms are existent, but when you apply quantum to it, to a greater extent, those faults are reduced. Then like that, Google's quantum supremacy claim, Chinese photonic quantum supremacy, ongoing scientific debate, part 2, practical quantum advantage, near-term targets, medium-term, like that, and all people have been defining and working towards that. Then current consensus, quantum supremacy achieved for specific artificial problems, practical quantum advantage still awaiting demonstration, focus shifting from supremacy to useful applications, right? That is the intention. So it should help the ordinary people, right? That is the final goal of whatever has been done so far. So therefore, though they're trying to tell that supremacy is achieved, ultimately it should help for your useful applications. Like phase-wise also that's been done. Major technical challenges, research priorities. If people want to write papers and publish the papers, they can choose one of the problem statement like post-quantum cryptography standards and implementation, like that and all. They can contribute towards like Shor's algorithms only. If you implement Shor's algorithm and introduce your own ideas in between and say that by this amount, this has been doing well, that will be a major breakthrough, right? Like that you can contribute. So this all depends on how research enthusiast one person is. Based on that, they can contribute it. So growing quantum startup ecosystem. See, more than 1,000 plus companies worldwide, they are having these startups. They are solely working towards these quantum technologies to providing solutions. Then corporate investment, all these things. Government is also investing, corporates are investing into this quantum technology because there is a feasibility of getting the solutions. Then key takeaways from today's session, I mentioned about quantum computing, which represent fundamental paradigm shift in computation, major algorithms, Shor's and Grover's also I mentioned, and Shor's example, with an example I explained. We demonstrated theoretical quantum advantages. Current NISQ devices are important stepping stones to fault-tolerant system. The major intention is reduce the noise. Noise is nothing but the errors, okay? So reduction in the errors. Say if you are transferred 11000, for example, if it is reaching as all zeros, so there is a noise, right? There is an error. So therefore, it should not be reached as all zeros or all ones. It should reach the destination as 11000 only. So integrity. So that should be maintained, right? So therefore, with respect to these things also, why this quantum technology can help? when it reduces within fast in a very, very fast way. So that is the intention. It should not be that once it is read, then you process it, then you send it to the destination. That is not how it should be. Therefore, on the go, the error correction algorithm should be working towards in the reduction of the noises. So current reality check. So we are still early stages of quantum computing development. Classical computers remain superior for vast majority of practical problems. Significant engineering and theoretical challenges remain unsolved. Timeline to practical quantum advantage uncertain, but progress accelerating. The meaning is classical computers are still there. It's not that quantum computers have taken over the classical computers, but there is a scope for quantum computers to pitch in because of its own advantages, which you have seen it, right? So they have demonstrated theoretical advantages. So we need to bring those theoretical advantages into computing advantages. When does the computing advantages happens? We need to have the processors, ALU, arithmetic logic units, etc., etc. So with respect to quantum, we need to have quantum processing units, QPUs, right? So GPUs, we all have understood, graphical processing units. CPUs we had, then GPUs. Now we need to have QPUs. That is the intention. What is the advantage of QPUs? We already seen it. Exponentially or quadrilaterally, the time is reduced, reduction in time. So just imagine how fast the things can happen, right? So it should be beneficial to the mankind. And evolving of new algorithms again. So far we have seen that cryptographic algorithms more secure, but we also seen that it is possible for quantum computers to break them within a fraction of a second kind of a thing. So therefore, they are no longer secure. Therefore, there is a need for more secure algorithms, quantum resistant algorithms. So like that is a challenging now. So that is where world is moving towards, right? That is the intention of learning all these things. One should know like where the world is leading to with respect to algorithms. So far, whatever we are having is not sufficient. So therefore, it has been moved to the next domains. That is quantum is one thing. Who knows, after quantum, something else will come into picture, right? Real time kind of a thing can happen. So like that is the thing as of now. So that is where people are working towards that. So these are all passion researchers who try to contribute. And of course, we all got to know about research and all those things very recently kind of a thing. And we started writing the papers. Just imagine the people in USA or like Einstein's place, etc. Einstein also studied in USA only. So they very high intellectual people are there in USA. I'm just trying to tell my perspective. It is my only perspective. Okay. So I'm not denying anything with respect to our India. Indians also have contributed majorly. We have seen Grover's algorithm. But the facilities, the way people think, the way the people approach, the way the people develop the algorithms is completely different. That is Bell Lab technology, right? So therefore, major inventions came through that. And the Stanford or Massachusetts Institute of Technology, they are the hubs for these kind of revolutionary inventions. So like that, it is happening. So let us appreciate that. And majorly Indians only are contributing majority of the things. So I'm trying to bring in, this is how, what is happening in the current world scenario, why people are talking about this quantum computing algorithms, right? This is the intention. Order of complexity is the intention with respect to time, with respect to space, right? So this is about all these things. So some questions like which applications are more likely to achieve quantum advantage first? How should organization prepare? What are the ethical implications? How will quantum computing change cybersecurity practices? What role will quantum computing play in solving climate change? All these things, right? This is what is important. Climate change, for example, something is happening in the near, say, tsunami is happening. By the time it reaches to the people, already people would have been drowned, right? That's not how it should happen. So real-time information should come. So therefore, quantum computing can help in those situations and save the lives of the people. So like that, you name it, all the applications are there. So some answers like optimization problems, which I already spoken, material science, machine learning, finance, cryptanalysis. Then how should organization prepare? Quantum awareness and education, just like the way you're all doing. So I think this is very interesting one. People should be aware of. post-quantum cryptography, hybrid computing strategies, partnerships and research, data governance and risk management, ethical and regulatory frameworks. It's not that if you use quantum computing is the final, it should be done kind of a thing. No, everybody should accept it. That is a major challenge. Every government should accept it. Regulatory framework should be there with respect to its utilization. Just imagine quantum computing falls into the hands of the hackers, right? So it will create the disasters. Just imagine like DDoS attacks, distributed denial of service attack. If it is taking 1 minute to attack particular organization, within fraction of a second, if it attacks that organization, just imagine usage of this quantum computing, right? So therefore, regulatory frameworks is also important. Ethical usage is also important. So that is how everything works in together. Then what are the ethical implications of quantum computing capabilities? Data privacy risk, digital inequality. We have seen that, right? Data privacy risk. RSA is no longer secure. It is breakable by these quantum technologies. So therefore, there's a risk with respect to data privacy. Then digital inequality. So some people, wealthy nations or wealthy people will have access to these quantum technologies, whereas non-wealthy nations or progressive nations still not able to access to that. Again, this is digital inequality. That should not happen in the real world scenario. Then weaponization. So quantum enhanced cryptanalysis or optimization tools could be used for cyber warfare, defense exploitation, destabilizing financial systems. There's a pro also and there's a con also. Pros and cons. Both the things should be looked into, right? It's not that, oh, quantum computing is helping us. No, quantum computing is helping us as well as it is not helping us. So this analysis is very important. Then intellectual property and fair usage of that is important. Environmental concerns is important. Like energy consumption of quantum system could increase, raising sustainability issues if not carefully managed. What is the meaning of this? We all know that every system is having a fan, right? Even your laptop is having a fan, your computer system is having a fan. Why? Because as the energy consumption increases, temperature increases, and it is susceptible to damage your system. Just imagine a data center which is having thousands and crores of systems built in or servers are running simultaneously, right? They will have cooling effects over there. Actually, if you really go through these data centers like Oracle data center or Apple data center or IBM's data center, which are all situated in USA, but the way that is being controlled, energy consumption, if you use quantum systems may increase, and how to sustain that, right? So again, the environmental concerns has to be looked into. Then ethical AI development should be looked into. All these things are the ethical implications. Then cybersecurity practices, already I mentioned about this, quantum key distribution, threat landscape, secure authentication, incident response, preparedness, when something happens, right? Because of quantum also something can happen. But how preparedness the organization is to tackle these kind of things, that is called as incident response preparedness. Say fire is happening in your home, right? What do you do immediately? You try to douse off the fire and call the, if it is very huge fire which is broken out, right? You cannot sustain that, you cannot douse off that. Then what do you do immediately? You will call the fire police, fire brigade, etc., right? If something happens, that is, we call it as an incident, and how to respond to that incident when we use this quantum computing also, right? In cybersecurity, we teach all these things. Incident response teams will be readily be available when something goes wrong. So that also is another aspect to be looked into when we talk about computing, this quantum computing. What role will quantum computing play in solving climate change? So like energy optimization, materials for clean energy, climate modeling, carbon sequestration, I mean, CO2 emission, right? So that should be sustained. Then supply chain optimization. All these things should be looked into. It's not that we have found proper quantum computing machine and we are now ready to run the machine. But repercussions of that, the pros and cons of that also should be analyzed, and that should be taken care by every organization, and the individual will be using that. So that's about my topic on quantum computing and algorithms. I hope to a certain extent I was able to cover what I wanted to tell to all of you. This is not the end of it, as I mentioned, right? So far, we started with the brute force techniques. We all have studied design and analysis of algorithms, right? We started with primitive kind of algorithms. We analyzed them with respect to order of complexity. Then we moved on to divide and conquer, where binary search we applied, right? So order of complexity increased to like log n to base 2. Earlier, it was order of n, order of log into base 2, which is like lesser than order of n, right? So like that, we moved on from one order of complexity to another with respect to that particular problem. Now, quantum computing is a big brother of all the algorithms kind of a thing, which I can tell. So we have already seen how much reduction it is happening, exponential reduction or quadrilateral reduction of time. This is where the advantages are. And disadvantage also we have seen pros and cons to be looked into, but majorly towards the advantage side, this could be used. So that is the intention of this quantum computing and the algorithms. So there are so many chat questions are there, I think. I don't know. I think it's majorly for attendance, I guess. If any questions are there, whatever I know, I'll try to answer.
Ma'am, some participants had been asked for the PPT to share it, ma'am.
Yeah, sure, I will.
Okay, sure, ma'am. Thank you, ma'am. And if any doubts, participants can ask. You can raise your hand and you can just unmute and you can just ask if any kinds of doubts you wanted to ask.
If any questions are there, see, it all depends on, we should be studying, like we should be more thorough with our data structures and algorithms, design and analysis of algorithms. That is how it goes on. Computer networks, cryptography and network security, cyber security. Then, because we are in computer science or something related domains, right? So we are not into those drug discovery, etc., etc. Those are in that domain. They can look into those aspects. With respect to, especially from computer science and engineering aspects, I'm trying to tell these are the very, very important things one should be knowing to understand all these things. So data structures algorithms, then design and analysis of algorithms, probability, then computer networks, cryptography and network security. Then when we learn these things, now we'll try to understand what they're trying to tell to us. So this is what my message that I wanted to convey to all of you. And keep reading, keep studying, and wherever possible, try to take these kind of subjects to be taught. When you teach, you learn more, right? So that is how I also have learned it. That's how I'm able to tell something about this. So this is how the things are. Teach them and understand them better. Okay.
Okay, ma'am. Thank you, ma'am, for your wonderful session. This was literally a wonderful session. I extend our heartfelt gratitude to our esteemed resource person, as Dr. Nalini ma'am here, and for sharing your valuable knowledge and practical insights. Your sessions was literally enriched our understanding and inspired, ma'am. Literally,
Yeah,
thank you so
you.
much, ma'am, for your session. And
Thank you.
we'll have the one more session, that is session 4 by
Yeah.
Dr. Selvi ma'am. So it will be starting at 7:30. So everyone be there on the Zoom meeting so that we can just start with the next session.
Yeah,
Thank you so much,
so
ma'am.
much, yeah, for the opportunity given. I thank Devi, Institute of Engineering Technology, and all the stakeholders of that esteemed institution. Thank you again. I will meet you all again in another session after 2-3 days, I guess. Thanks for the opportunity. I will be exiting this session now. I wish all the best to all the participants.
Sure. Thank you so much, ma'am.
Thank you.
I request all the participant, the session feedback link or attendance has been shared in your chat box. So kindly give your valuable feedback and give your attendance right now.
Good evening, Chetan sir. Could you please share the PPTs of yesterday's and today's sessions?
Yes, ma'am. I will going to collect it and share to you, ma'am.
And then it will be useful for us when we are trying to recap. Thank
Sure,
you.
ma'am. So I'm going to be coordinate with our coordinator. So once the ma'am is getting the all the sessions PPTs, so definitely going to share in the WhatsApp group, ma'am.
Thank you, sir.
Thank you.
I request everyone to give the feedback that has been already shared in the feedback link in the chat box, and even to give the attendance so that will be listed in your attendance list. Thank you. I hope everyone had filled the feedback, and for the first session, that's the third session, first session of today's D2, and the attendance. So we are going to start with the second session, and I'm here so proud to invite our guest, resource person, Dr. S. Selvi ma'am, here, who is the associate professor and head of the department in Department of Artificial Intelligence and Data Science in Kangayam Institute of Technology, Nathakadayur, Tirupur district, ma'am. She had a educational qualification like PhD in the CSA in Anna University, Chennai at KSR Institute of Engineering and Technology, Tiruchengood in the year 24 in the year 2019. And she had done the title that is Novel Optimized Rescheduling Algorithms for a Multi-Layer Cloud Environment. So this was her work. And she have got the awards and achievements as the reviewer in Journal of Internet Technology, and she was like a reviewer in IGI Global Platform. She was honored with Best Faculty Award in the year 2013 by Angel College of Engineering Technology, year Tirupur, and she had received literally 100% result of achievement award in the subjects like open source software, cloud computing, PC hardware and troubleshooting, software project management, web technology, distributed computing, cryptography, and network security at Angel College of Engineering and Technology in Tirupur. And along with that, she had even received 100% of result in achievement award in the subjects like advanced computer architecture, software testing, cryptography, network, and security at Sausuri College of Engineering, Vijayamangal. And she had a lot of professional experience where it's been around 20 plus years of experience in the teaching. That's a professional experience, and she had a lot of works in publication. Like she had done, ma'am had done international journals in the publications like the International Journal of Engineering and Innovative. In the year, it was published in 2012. The title of the work is Dynamic Steady State Distribution in Cloud. And even a lot of publication, ma'am, Dr. Selvi ma'am had been done. She had published more than 25 plus of journals. So it's so proud moment, ma'am. And I'm so proud that I'm here as a participant, and I'm so feeling proud that I'm welcoming you here, ma'am, for this session. So it's over to you, ma'am.
Thank you, ma'am. Thank you for the introduction. Am I
Thank you,
audible?
ma'am.
Am I
Yes, ma'am.
audible to all?
Yes, ma'am, you are audible, ma'am.
Okay. So first of all, before going to the session, I would like to give my gratitude and thanks to Sridevi Institute of Engineering Technology for giving me such an opportunity to share my views on quantum gates and circuit models. So, as the resource person, the previous session said, so we, the teacher, we are going on updating. As my PhD experience is on cloud computing, I have been shifted gradually from cloud computing to machine learning and deep learning, and now I'm shifted to quantum computing also. So, I want to
Sorry,
give
ma'am.
thanks to-
Excuse me, ma'am. Sorry for
Sorry for
interrupting,
the
ma'am.
Is it
Actually,
audible?
your voice is quite not proper, ma'am. Actually.
Is it audible now, ma'am? Is it audible?
Yes, ma'am. It's audible, ma'am.
Okay. If I'm not getting audible, please interrupt and say me, ma'am, so that I can.
Sure, ma'am. Actually, it's giving some kind of echo voice, ma'am.
Okay. I think.
The mic issue
Okay, let me
somewhere.
check.
Okay, ma'am.
Okay, let me check. Okay, ma'am, just shall I share my screen?
Sure, ma'am.
Is it visible, ma'am? Is it visible to all?
Yes, ma'am. It's visible, ma'am.
Okay. Today my session is about quantum gates in circuit models. So myself, thanks to the introduction,
Sorry
and
for the
myself,
disturbance,
Doctor.
madam. Your
Still,
voice
I'm
is
there.
not
Still not
coming.
audible. I'm still not audible.
Your voice is stucking, ma'am.
Okay, is it audible now?
No,
Ma'am,
ma'am.
you are
It is
audible, but
stucking.
some disturbance is there in your microphone or something like that. You can check, ma'am. You can have something like one
Okay,
minute.
Madam, you
1 minute.
might have used Bluetooth or something. Please check it.
Yeah,
Bluetooth device.
Bluetooth. Yeah.
Yeah,
Yeah, I
the
have
problem
used
with the Bluetooth
Bluetooth.
device, madam. Please change it, then it will be okay.
Okay, let me check. Let me. Am I audible now?
It is clear
Yes,
now.
ma'am.
Yes.
It's
Thank
clear
you.
now, ma'am.
Yeah. Okay, thanks. Okay, let me go directly to the session. Yeah. So today my session is quantum gates and circuit models. Before going into the session, I would like to give an introduction about certain informations regarding quantum computing and what is a qubit and what are the principles we are going to there are in quantum computing. Next about Bloch sphere. Next, quantum gates and its operations, the types of quantum gates, the single qubit gates and multi-qubit gates, and a small circuit diagram example. Okay. Yeah, before going to what is quantum computing, I should say what is quantum, right? So a quantum is nothing but a small packet of energy. So you all know what is quantum. It is very really fast, very fast when compared to the classical computers. But you should know what is quantum. It is just a small packet of energy. Because the quantum computing it is extracted from quantum physics. So it is emerged from the quantum physics, and here it has just a small packet of energy. So here you can see there are three properties of quantum computing: the wave particle duality, superposition, and quantum entanglement. Okay, so why I have said as quantum physics? Because the quantum revolves around the waves and particles. Okay, so quantum computing is a computer that exploits quantum mechanical phenomena. So it is totally on the base of quantum mechanics to perform the calculations faster than the classical computers. So it leverages both the properties of particles and waves. You all know what is a particle and what is a wave. So particle, you can measure it. You can measure the distance of a particle. You can measure the position of a particle by using an x and y coordinate. Whereas when you're comparing to a wave, when you're coming to a wave, so a wave is immeasurable. So it's just like a thing which is in the ocean of or the sea. So you couldn't measure anything in the waves. So it will be dispersed everywhere. You couldn't measure where it is going and where it is passing through and everything. Okay, but this quantum computing, totally the principle lies beyond lies in the combination of waves and particles. So because so such there will be such a fast manner. So it'll act both as a wave and also as a particle. So it will be solving, we'll be able to solve complex problems. So this is one of the reason why the quantum computers can be able to solve very complex problem in a minute of matter of time. Okay, so even a classical computer to solve a problem, if it is taking thousands of years, so by using quantum computers, you will be able to solve that problem in a matter of 10 minutes, because you all know how waves will be very fast, right? So the same principle is being used. So we can go with an example. Okay, so let us take a suitcase. We can go with a simple example. Let us take a suitcase with a number lock. Okay, so when you're using a classical computer and you consider that is a number lock with a two-digit number. Okay, so for example, the key to open a lock is 10. You consider that key to open a lock is 10, but you are not having, you are not remembering about the number what you are given. So then what you will do, you will be trying out the n number of possibilities to open that lock. So when there is a two-digit number, there will be four possibilities. Okay, so then you can go with, there are the possibilities like 00, 10, 11, and 01. Okay, so when you are able to solve this problem by using a classical computer, so what the classical computer will do is, it will first solve by using the combination of 00. So next it will be able to solve, if it is a wrong lock, then what it do is, it will try to solve it by using the next combination 1 1. Next, if again it is also a wrong, then it will go with the next combination 01 and 10 something, so like this. So it keeps on trying until you're getting the correct clock number. Okay, this is in the case of classical computers. So here you'll be taking at least 4 seconds to unlock to unlock a suitcase. Okay, when you're coming to a quantum computer, so here you'll be using a principle called superposition, so that we can see elaborately, but I'll just give an intro about it, how quantum computer works. Okay, so in this, the quantum computer will try with all possibilities of the combinations at the parallel time, in the simultaneous manner. So that property is said to be superposition. That is, it is able to solve all the possibilities in the same time. Okay, so automatically it will take only 1 second to try all the possibilities in a parallel manner, and it will be able to unlock it. Okay, so next we can come with the quantum interference. It is also one of the thing, because so everywhere you know that it is a base and a particle. So it will be able to inculcate all the possibilities within a given time in a parallel manner. That is the property of quantum, that is waves and particles will be incorporated in solving a problem simultaneously. So that comes the quantum interference. So I can say, how a quantum computing exists, that I can say by using a simple experiment. So that experiment is said to be a double slit experiment. So which was being discovered by the scientist in the initial stage itself, how the quantum computing emerges. Okay, so consider there is a electronic gun. Okay, so if an electronic gun, they are going to shoot electrons. Why I'm saying about electrons? Because it is a particle. So it is a combination of particles and waves. Automatically, the particle will be comprised of electrons and protons. Okay, so you consider an electron gun, and there are certain slits available in front of the electron gun, and the electron gun, you are shooting the electrons one by one. So when you are doing like that, so what in the quantum computing, so I am going to explain you what is the working principle behind quantum computing. So when the electronic gun is shooting it, automatically, so initially, here I said you double slit experiment. That is, there are two gates. Okay, two gates. In the first gate, there are two slits, there are two openings. And when the electron is being injected, so automatically the electrons will be passing through the slit, which is open in the first gate. Okay, so and after when it passes after the first gate, it will be going to the second gate. So in the second gate, what the property, so that the distance, or the distance between the electronic gun and the first gate is, it will act as a particle. So I have said you electronic guns, electron shots, so that will be in the form of a particle. Whereas when you're coming to the second gate, the distance between the first gate and the second gate, so there the particle will be disguised as in the form of waves. Okay, it will be disguised in the form of gas, and it will be dispersed everywhere. It will be dispersed everywhere, and it will be striking anywhere in the second gate. Okay, so there will be a number of openings may be there. So it will be pausing on very furiously, and it will be hitting the wall or hitting the next gate. Okay, in the form of waves. So there is a combination of gates and particles. So a few times it will be acting, at certain times it will be acting as a gate, and at certain times it will be acting as a particle. So this is a double slit experiment. So only by this nature, the scientist is able to come to a conclusion that the quantum is nothing but it is a wave particle duality. Okay. Next, you all know, you might have attended this previous sessions, and you might all know about classical books and quantum base. But I'll say in my own teaching methodology. Okay, so here when you're coming with the classical bits, you all know that there will be two bits. It will be 1 and 0. So if it is 1, it is an on state, and if it is a 0, it is a off state. Okay, whereas when you're coming with the qubit, so the 1 qubit is equal to 2 bits. So it is an equivalent. The 1 qubit is equivalent to a 2 bits. So automatically the bit 0 is represented in the form of a 2 bits in a qubit. So 1 qubit you can represent with the form of a 2 bits. That is, the length of the qubit is 2. So it will be 0, 0, 1, 1, 0, 1, and 1, 0. So among all these things, the 0 can be equivalently compared with double 0. 1 will be equivalently compared with double 1, and the superposition. I have said about the superposition, no? So in that superposition, it will be maybe 0, 1 or 1, 0. So it can be in any one of the format, so that it can be 10 or 01. So I'll give you one more example regarding superposition also, because you consider you're tossing a coin, right? You are tossing a coin, and you consider there is a twin coins. That is, there are two persons. One is in India, and the other one is say maybe in some other abroad, maybe some London. Okay. So when you're slitting the coin, when you're sliding the coin, tossing a coin, so what it happens is, initially by using a classical computer, the two persons, one in India and one in America or London, so they are tossing a coin at the same time. So whereas in a classical computer, so if you want to identify what type of result has been, there is a coin has been tossed, whether it can be head or a tail. Using a classical computer, what will be the scenario? So the scenario will be in such a way that the first person in India, he will be identifying his coin is the his coin will be a head or a tail. Similarly, he will be making a video call or a phone call, and he will be asking the second person in London, what is the coin being tossed by you? Okay, so that may be head or tail. So this is a series of actions. What is implemented by using the classical computers. Okay, whereas in quantum computers, what there will be taking place is, the coin is being parallelly tossed by the two persons, and automatically the first person in India, he will be able to identify the coin is head. Automatically, without making a phone conversation or any means of conversation to the second person, the first person can be able to identify what is the coin being tossed by the second person in London. Okay, so he will be able to answer the second person has got a head or a tail. Okay, so head. So that without me any means of communication with the second person, so the first person can be able to say whether the second person has got the head or a tail. So this is said to be a superposition. Okay, so similarly, so I'll give it one more example. You just have a hummingbird. You all might know about a hummingbird, and hummingbird will be flopping its feathers, right? It will be flopping its feathers while it's flying. So it will be flying up, and the feathers will be going up and going down, and it will be in the middle of the thing and everything. So you can just compare it with the bits. Okay, so when the feather is going up, you can say that is a up state or on state. When the feather is coming down, you can say that is an off state or one bit. Okay, so in the intermediate level, when the up and down state, there will be a middle level, right? So in the middle level, you cannot be able to say whether it is a 0 or 1. So whether it will not be able to say whether that feather is going up or down. So it will be frequently flattering its feathers. Okay, it will be in the middle state. That middle position, you will be saying it as a superposition. Okay, so can you able to identify or reach the point how the superposition works? So you will not be able to predict. You will be able to predict the same up and down. Okay, in the middle state, you can say it can be either up or an up down or down. So that state gets always varied. It will be varied. Okay. So this is also one more example. So the same what I have explained you now. So that is explained by using in this scenario, in this figure. Okay, so in the first figure, you can say that I'll come blood spear. You are might have learned in the previous sessions. So here blood spear. So the result may be either 0, 1, 1. This middle state, so this middle state can be either 0 or 1. Okay. Similarly, what I have said you, the coin tossing a coin. Okay, so this it can be either 0 or 1. So I'll just maximize it. So you can see here the position or the 0 and 1. The coin can be either 0 and 1 at the same time. So that you can say it is a superposition. Okay. So qubits can take the same value simultaneously. So these characteristics will be providing you the possibility, that is the possibility of either 0 or 1 at the same time, Okay. So based on this, you can come to some parallel communications, calculations, computations. So due to which you can perform the computations in a very faster manner, very faster manner when compared to the classical computers. Okay. Next is the quantum computing principles. So this I have explained you. The first one is superposition principle, the quantum entanglement, and the third one is tunneling effect. Okay. The superposition principle, now I have explained you what is superposition in principle. Next is quantum entanglement. So I'll say, okay, I'll go with the superposition principle. So this superposition principle can be represented by means of a Bloch sphere. Okay, so it is a sphere, it is a Bloch sphere. So this Bloch sphere will represent you the bits. Okay, so in the top of the upper part of the sphere, you'll be having the 0 bit. Okay, and the down part of the sphere, you can be having a 1 bit. Okay, and the middle part of the sphere, so that it will be either 0 or 1. So the 0 1 can be in any part of the surface of the circumference of the Bloch sphere. So there are many possibilities here. Okay, so the 0 or 1, so that will be lying in the middle part. Okay, and this Bloch sphere can be represented in the form of 3 coordinates: x-axis, y-axis, and z-axis. Okay, so why I'm coming back, explaining about the axis is based on the axis value, there will be a superposition value, and also there will be a process of entanglement. Okay, so here each qubit state. So all the surface of the Bloch sphere will represent you the state of the qubit. Okay, so it will be any state of the qubit, and the state of the qubit, it can be represented by means of 2 complex numbers. Okay, so I have said you the upper part is represented by means of 0 bit, the down part is with one bit, and the middle part totally it will be in the superposition. The superposition, either it will be 2 bits, it can be either an 0 or 1 at this 0 and 1. It's not or 1, it's 1 and 1 at the same time in a simultaneous manner. Okay, so here the surface of the sphere will be representing the possible pure states of the qubit. Okay, while the interior of the sphere will represent the mixed states. So the interior of the sphere will be representing the mixed state, and the surface of the sphere will be representing the pure states of the qubit. Okay, so actually the qubit state can be represented or described by means of 2 complex numbers. So you all know what is the structure of a complex number. It is a real part per imaginary part. Okay, so the complex number will be having automatically a real part and imaginary part, and from this the real parts can be represented or can be determined a point in any part of the Bloch sphere. Okay, so the real part is there, no? That real part can be represented, it will be determined or calculated by using a point on or in the Bloch sphere. Okay, and here I have said you 3 coordinates: x-axis, y-axis, and z-axis. The x-axis will be representing the real part of the vector, that is a qubit state, and the y-axis will be representing the imaginary part of the qubit state. And whereas z-axis will be representing the probability of the qubit, which is measured by using either it can be 0 or 1. What I'm trying to say is the z-axis will provide you the superposition value. It can be either a 0 or a 1. Okay, so based on this, based on the quality, that property of superposition, the qubit will be able to perform multiple operations in a simultaneous time, and it will be more faster. So this is the reason why it is more faster than the conventional computer. Okay, so when I'm coming to the mathematical representation of the the formula of the Bloch sphere. So here you all know, in a classical computer you can represent by means of the bits 0 and 1, right? Whereas here you'll be representing the bits by means of cat 0, cat 1. So you have parallel a line followed by 0 followed by greater than symbol. So that you'll be seeing as cat 0, and a line with followed by 1 followed by greater than symbol, that you will be saying is a cat 1. Okay, so this you can get the possible values of the complex numbers by using the formula called alpha cat 0 plus beta cat 1. Okay, so this is the formula. So this what is the symbol pi? So it is a symbol pi. So pi will provide you the value of alpha cat 0 plus beta cat 1. And why we are representing the symbol by using pi? Because pi is a representation of the waveform. So wave can be represented by means of a symbol called pi value. So we are using here. And all these things, you can come to a similar to a probability value. So combination of all probability values, you will be coming to round up to 1. Okay. Similarly, here also alpha square plus beta square will be always equal to 1. So the arbitrary point, so any point on the surface in the block can be represented by using a pi equal to cos theta by 2 cat 0 plus e power I pi into sine theta by 2 of cap 1. So why I'm not going deep into this how this formula has been derived, because it may take a number of time, it may take a prolonged time. So I'll give you when you the any point in the middle part of the surface of the blosphere, you can represent by using this formula. Okay. So next, quantum entanglement. So this quantum entanglement is nothing but both gates. That is, I have said, the first person in India will be able to guess what is the value in the value. There's whether head of the tail of the second person in London. So that is quantum entanglement. So the reflection of the second person value will be automatically reflected by the first person. So now you can represent or compare this with the quantum computing. Okay, how it means is there are two operations that has to be performed in a parallel manner. Okay, so the first operation is going on, the second operation is also going, the multiple operations are going on in a simultaneous manner. Whereas now the entanglement is the value of the second operation will be automatically reflected in the first operation, and the value of the first operation will be automatically reflected in the second operation. So automatically reflect without any prior communications or with some messages, communication messages. This everything are some using some packet transmissions or protocols. So this everything is not by explicit packet transmissions. Okay, so the first operation can be able to predict the value of the second operation, and the second operation will be able to predict the value of the first operation. So by using this, you will be able to process the operations in a simultaneous manner. So the parallel processing of the information. So the same thing, the entanglement. So here, if it is a bit, you can represent the entire bit can be either 0, 100%, and the entire bit can be 100%. Whereas when you are coming to a qubit, so the qubit, there will be a superposition operation. So that superposition you can represent by means of cat 0 plus cat 1 divided by root 2. Okay, so this is the value of the superposition. Whereas when you're providing an entanglement, so that entanglement that you can represent by using the formula called cat 00 plus cat 11 divided by root 2. Okay. Next, tunneling effect. Okay, so if it is a, you all know that automatically if there is the conventional, just a normal example I'll provide you. If there is a tunnel, so a person is trying to climb the tunnel, he will not be able to climb that, he will not be able to intrude the tunnel. I intrude inside the tunnel and go to the next side of the next side end of the tunnel, because so that is not possible, right? The same thing is reflected in the classical computer. Okay, so it will not be able to. So if it is a classical physics or classical, because the conventional computers will be purely dependent on classical physics, and the quantum physics will be the source, or will be the prerequisites and the source for the quantum computing. Okay, so if it is a conventional computer, so that will follow the principles of classical physics. So where that if there is a tunnel or if there is any barrier, so it will not be able to intrude within that and able to get into that and intrude it and provide a solution. Okay, whereas in quantum physics, so I have said you already, it is a particle wave combination or a duality. Okay, so as a wave, so till tunnel, the quantum qubit will be taking the form of a particle, and when there is a tunnel now, automatically it will be intrude inside the tunnel in the form of waves. and it will be able to come outside. So that means how you can reflect this one, compare this one with the quantum computing is, so wherever possible, whenever possible, and in any part of the states, the quantum computing will be able to solve any type of complex numbers. Okay, so it will include in every nook and corner and will be able to solve the problem. Okay, so similarly, if a ball is there to pass, if there is a conventional computer, the ball will get bounced against the wall. Okay, if it is a quantum computer, it will be going intrude into the wall and it will be coming out. So that is an description of this diagram. Okay. The same thing, one more diagrammatic explanation. Here I have given you in the form of quantum mechanics. Okay, so when there is a barrier, so the first one is the first one we can say if it is a ball or something now. So the first part, the second diagram you can come, the second diagram you can see that energy versus velocity. Okay, so potential energy and the barrier. Okay, so in the first side in the form of a waves and particles. So in that time, the particle energy will be greater than the potential energy of the barrier. Okay, so in that case, so when the particle energy is greater than the potential energy of the barrier, the waveform will be very smooth and continuous, and everything the particle will be in so it will be the form of a particle part. So on this time, so here it will be in the form of a particle form, and it will be intruded. It will be coming in a smooth operation. Whereas E less than V. So when the particle energy is less than the barrier, okay, well, less than the potential energy of the barrier, so it will transform the particle will be transformed into a wave, and it will intrude into the barrier, and it will go out of the barrier. Okay, so the wave doesn't will not immediately drop to zero, so it will diminish the total amplitude. So the total amplitude of the particle that will get diminished to zero, and it will went through the barrier, and again after the barrier it will again convert into a particle. Okay, so there again the wave emerges from the other side of the barrier, and there will be a lower probability of the particle on the other side. Okay, so this I have sent you the plot sphere. I have said the same diagram, but here I have said you the complex numbers. The complex numbers, so it will be in the form of that you all know, right? Complex numbers in the form of real part plus I into the imaginary part. Okay, so that I have represented here. This is the geometrical model, represents the pure state of the single qubit. Okay, so the state zero, the same thing what I have explained you there. So that same thing is here. So here there are three, how the angle gets measured. Okay, so that is clearly explained in this slide. So the amplitude alpha and beta we represent by the spherical coordinates. So they are represented by the spherical coordinates, and the using the theta and the polar angle due to the lack of time. But you should know about polar angle and what is azimuthal angle and everything. So the amplitudes, what I have said, that is totally represented from mathematical part. Okay, so alpha and beta, the amplitudes will
Excuse
be
me, ma'am.
the sum of a
Excuse me, ma'am.
yeah.
Sorry, ma'am, for interrupting. Actually, ma'am, your voice is breaking, ma'am.
Okay. Is it okay now?
Yeah, it's okay, ma'am. It's clear now, ma'am. Thank
Okay. Okay. So there is a network connection, deviations in my network connections. Okay. Now is it
Yeah,
okay?
it's okay, ma'am. No issues, ma'am. Thank you.
Yeah. Okay. 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 So I said, the polar angle theta and
Hello,
azimuthal
ma'am.
angle,
Sorry,
and
ma'am.
it will be expressed of
Again,
the
it's
same thing.
the same thing, ma'am. Yeah.
Pi equal to alpha cat 0 plus beta cat 1, and totally the probabilities of the measuring the qubit will be alpha square. Pardon? Okay, I'll just change my position. You say, is it okay now?
Yes, ma'am. It's okay,
Ma'am, is
ma'am.
it audible?
It's audible, ma'am, now. Thank you, ma'am.
Okay, ma'am. Okay. Okay. Okay, the probabilities will be measuring the qubit. So that is alpha plus beta modulo of alpha meter square is represented by means of a Bloch sphere. Quantum gates. Now we can go with the exact session, that is quantum gates. So the quantum gates are nothing but it is a unitary operations. We'll be saying as a unitary operations. I'll just say you, it is just a mathematical operators. It will be manipulating the state of the qubit. So just now I explained you the qubit states, right? So that qubit state, or you can get it similar to a classical gate. So such as NOT gate, AND gate, NAND gate, XOR gate. So similar to the classical gates. So here also the qubit states can be represented in the form of a mathematical operators. Next, that is, you can rotate the state vector of a qubit inside the Bloch sphere. So you can just relate the gates with the Bloch sphere. Okay, so whenever you're rotating or you're transforming one vector or one state to another state of the qubit, so that will be reflected in the Bloch sphere. So this ability will be existing in multiple states at once. We'll be giving the computer, the quantum computer will be tremendous power. And one more thing, all the quantum gates will be in reversible nature. So I'll explain you the difference between the classical gates and the quantum gates. Because, quantum classical gates, AND gate, OR gate, and everything. So when you're providing n inputs, you'll be providing you only one output. Okay, you'll be getting one output gate. So that is in case of classical gates, whereas that is which is represented or which is available in the classical computers. Whereas when you're coming to the quantum gates, when you're providing n inputs, you'll be getting n outputs. Okay, so n input, you'll be getting n output, and the same number of input will be equal to the same equal number of its output. So I have said you it is a unitary operation. Unitary operation that you can represent by means of there is one-to-one mapping. It is similar to a one-to-one mapping. Okay, whereas classical gate is many to one mapping, whereas in quantum one-to-one mapping. Whatever input you are there, that will be for provided to the next it's equal. Next, it is reversible, right? So why it is reversible? That is, it can come to its original. So when it is an output state, it will be when a qubit is in one state, it will be able to come reverse to its original state or its previous state. So that is possible. Okay, so there you can that state you can that is being due to the proper superposition and entanglement. Okay, so these you all know, this classical gates, NOT gate, XOR gate, and an AND gate. So if it is a NOT gate, flipping of the input. So whenever you are having an input as 1, you will be getting an output as 0. And whenever an input is 0, you will be getting an input of 1 in case of NAND gate. Not gate. And if it is an XOR gate, you can say that when two bits are 1 or when two bits are same, if both the bits are 0 or if both the bits are 1, you can say the output will be 0. And if if both the inputs are different, then only you will be getting the input as 1. So this is in case of classical XOR gate. And in case of NAND gate, just it's reverse, that is opposite of the AND gate. So if it is 0, 0, 0, 1 and 1, 0, you'll be getting the output value as 1. And if it is 1, 1, you'll be getting the output as 0. So this you all know. But why I'm going is, I will be going with the next one. Okay. The quantum gates I have said you, it is represented by the unitary operators. And there are two types of gates, single qubit gates and 2 qubit gates. There are also multi-qubit gates that is also available. So multi-qubit gates is nothing but 2 qubit gates is said to be a multi-qubit gate. That is also a multi-qubit gate. So multi-qubit gate can be 2 or more qubit gates. Okay, single qubit gate it is only a single qubit. It is only one bit. So if it is a single qubit gate, it will be flipping a qubit from 0 to 1. That is, there will be a flipping. Flipping is nothing but just like an inverter or NOT gate. It is represented by means of a NOT gate, classical NOT gate. Similar to a classical NOT gate. So here, when you are flipping a qubit from 0 to 1 or 1 to 0. Okay. So here there are types of single qubit gates. So there are poly X gate poly Y gate, poly Z gate, and Hadmot gate. So these are the basic single qubit gates. And types of multi-qubit gates, the control NOT gate, that is C naught. Next, Toffoli gate. Okay, I'll explain you one by one. So the first one is single gate. The single gate, you will be say, you can represent by means of the single qubit. The single qubit can be either 0 or 1. It is represented by means of CAT 0 and CAT 1. So you shouldn't write directly the 0 and 1 as like classical bits in quantum computing. Here the qubit should be represented in the form of a CAT symbol. CAT symbol is nothing but a line followed by the 0 or 1 followed by greater than symbol. Okay, now here is a column vector. So this is a vector. I have said you state vector. State vector is nothing but the CAT 0 can be represented by means of 2 bits. Okay, so I have said you the superposition. The superposition is the qubits. The superposition can be either 0 or 1, 0 and 1, and 1 0. So I have said you in the previous slide, in the previous initial slides, that if it is 0, if a classical bit is 0, that is represented by means of double 0 in qubit. If it is 1, that is represented in the form of a double 1 in qubit. Whereas if it is superposition, then the qubit can be represented in the form of 1001. Okay, so that is here. The CAT 0, the CAT 0 will be equivalent to a 10. That 10 you will be represented in the form of column vector. So there will be no row vector, it will be a column vector. Okay, next CAT 1. This CAT 1 is also represented, is equivalent to 0, 1. So I have said you superposition, no? That superposition, there is 1 0 and 0 1. That 1 0 is equivalent to CAT 0. The value of CAT 0 is 0 1 0 and the value of CAT 1 is 0 1. Okay. Now the quantum gate. I have said you the poly quantum gates, poly X gate, and the poly X gate is flipping an input gate from 0 to 1 and 1 to 0. Now the X of 0, that is X is nothing but poly X and CAT 0. So in the poly X, if you're giving an input 0, that will provide you the output 1, CAT 1. Okay. Similarly, in the poly X gate, if you're providing the input 1, it will give you the output as CAT 0. Are you able to follow me? So this is the very, very basic. So because if you're not able to understand the single qubit, particularly poly gate, then you will not be able to follow the remaining gates because this is the very basic gate. So you should know what is CAT 0, what is CAT 1. So these two can be CAT 0 is nothing but 1 0 and CAT 1 is equal to 0. Okay, and flipping the values. Okay, so both the things will be represented and it will be the poly X gate will be flipping the input to 0, it will be CAT 1, and if it is CAT 1, it is CAT 0. Next, 2 qubit gates. Okay, 2 qubit gates, you all know there are, if it is a 2 qubit gates, there are 4 possible positions. Okay, there are 4 possible positions, and here you are coming with the tensor products. Okay, you are tensor operation. So CAT 00. So here the 2 qubit gates are nothing but 00. So in will be represented for CAT 0, CAT 1. Whereas in 2 qubits will be represented by means of CAT 00, CAT 010, CAT 10. Now, how will you represent mathematically in the form of a state vector? Now, CAT 00, that can be equal. That how will you get the state vector? CAT 0 into tensor product of CAT 0. So, performing the tensor product, you can go with the matrix multiplication, and similarly, because CAT 0 represents by means of column vector and column vector 10, tensor product of column vector of 10, you will be performing the matrix multiplication, and finally you will be getting the value. Okay, so that 4 values also you're representing by means of column vector. That is 1 0 0 0 0. That is 1 into 1 1, 1 into 0 0. Okay, the second value is 0. Similarly, the second 0, 0 into 1 is 0, 0 into 0 is 0. Are you able to follow this? So you are likewise you are getting the other values also. So 0 1, the 0 1 can be represented in the form of a tensor product of 0 CAT 0 and CAT 1. Okay, so that is equal to CAT 0 you can represent by means of 1 0 and tensor product of tensor product of cat1. Cat1 is 0, 1. Now we have to perform the tensor multiplication, that is matrix multiplication. Now 1 into 0 is 0, 1 into 1 is 1. Okay. Next 0 into 0 is 0, 0 into 1 is 0. Similarly, you have to perform the all the values. Is it clear? So now what you have done, you have performed the tensor product, the two cubic states, in a two qubit system, you have to perform the tensor product of the single qubit states. Okay. Next, a 3-qubit system. Okay. So if it is a 3-qubit system, there will be a possibility of 8 values, 8 possible states. If it is a single 2, okay. If it is 2 power 2, then that will be nothing but 4 states. Okay. If it is a 3-qubit states, it is a multi-qubit state. Just an example alone. If it is a multi-qubit state, that multi-qubit state you can represent by means of 3 digits. And if it is 3 digits, it is 2 power 3, it is 8 values. So similarly, you have to perform the tensor values. Okay, tensor product you have to apply. Next, it is poly-X-gate. How it is represented? So the poly-X-gate is nothing but it's equivalent to a classical NOT gate. I have said you before, no? So it is a NOT gate. That is, you're flipping the input to its output. It's other side. That is, if the 0 cat, it will be cat 1. If the input is cat 1, it will be cat 0. That is flip. So transforming into this other side. It is a classical gate. X can be represented by means of the sigma x. It is represented by means of sigma naught, that is equal to 1, 1, 0. It represents of the matrix format. Okay. Previous slide I have showed the column vector. That is in a vector format. And now I am representing you by means of the matrix format. 0, 1, 1, 0. Okay. Next, poly Y gate. Poly X gate of Y. So what it will do is, so poly Y gate, it will map the cat0 to IF1 and 1 to IF0. Poly Y gate will be taking care of imaginary part of the complex number. I have said about the complex numbers, right? In the complex numbers, the poly Y gate will be taking responsibility of converting the input value into its imaginary part alone. Okay, that is, for example, cat0, it will be converted into the imaginary part of cat1. And cat1, it will be converted into the imaginary part of cat0. Okay, so y, capital Y equal to sigma y, that is equal to 0 minus I 0. Because the conjugate of y is plus I, conjugate of plus I is minus y, and minus I or the conjugate one, it is plus I. Okay, so it is it is similar to an identity matrix. You all know about identity matrix, right? If it is, what is an identity matrix? The identity matrix, the diagonal values will be equivalent, will be, whereas just opposite is the quantum values. Here, the identity matrix is here, it is not similar to an identity matrix. That is, the diagonal values will be 0. Okay, the diagonal values will be 0. Here, for NOT gate, the diagonal value is 0. And in poly, diagonal values are 0. Remaining to be the imaginary values I and plus poly. The point is, leaves the basis to 0 unchanged. You just listen here. The basis to say when you're providing a cat1, that will transform into a -1. Show you visual representation also. Next, Hamdat gate. This Hamdat gate is solely responsible for providing the property of superposition. Okay, so it totally shoulder the qubit order property, that is superposition qubit will be taken solely responsible by the Hamdat gate. Okay, so the Hamdat gate is a single qubit operation that maps the basis state of cat0 to cat0 plus cat1 root of divided by root of 2 and 1 cat1 to cat0 minus cat1 divided by root of 2. Okay, so this is solely responsible to provide the superposition. Okay, so how it is represented by means of the H is equal to my 1 by root 2 into matrix. It's 2 by 2 matrix is 1, 1, 1 minus 1. This is the actual value, right? So this how evolving everything I'll show you. That also I will show you. Next is poly scale. This we have seen it, no? The poly. So I have said you it is a reversible one, right? I have said you it is a reversible one. It is synonymous or equal to a classical reversible nature. So it is matrix represented as U naught. Since it is a unitary operation, is nothing but it is a reversal. The reversible nature is represented by means of net operator. Okay, so it represents the previous slide. Next, U naught of 0. At 0, that operation 0, 1, 1, 0 into 1, 0. Be providing 0, 1
Ma'am,
after
ma'am,
performing matrix operation.
Sylvie, ma'am,
Okay,
Sylvie, ma'am.
ma'am. Okay, sir. Tell me, sir.
So sorry for interruption. Ma'am, your voice is not cleared, ma'am. Please kindly check it once.
Now, also, is it not clear?
Now it's clear, ma'am.
Till
But
now, is it
some
clear?
now it's okay, ma'am.
Till
Okay,
now,
can you
is it
speak
clear?
now?
Yeah,
Okay,
till now,
earlier it was
is
your...
it clear
No,
for you?
No, it's something noisy was coming.
now it's clear, ma'am. In between, sometimes there is network leakage, ma'am.
Okay. So whenever you are getting some issues uh, in my
Sorry, ma'am.
or
Again, there's a network issue, ma'am. Can you just check with your network, ma'am?
okay. So next is X. Is it okay? Wait a minute. Is it okay, ma'am? Is it audible now? Is it clarity? Are you getting
Uh,
clarity now?
yes, ma'am. The voice is clear, ma'am. But
Are you
the
getting?
camera.
Okay.
Sylvie, ma'am, kindly share the presentation
The
because
I think
where
presentation,
you're
I'm
ma'am.
showing
finding.
something.
Pardon?
Now, kindly share the presentation. Actually, you're what you're going to share you're going to
Okay.
on the video. No, you're going to display your house. I think.
Okay. 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 Let me change the position. Give me 2 minutes time. Voice kickler. Voice kickler. Voice kickler. Voice kickler.
You can just mute yourself and you can just correct out the network issues, ma'am.
Ma'am, is it audible now?
Yes, ma'am. It's audible, ma'am, now. Voice is
Okay,
audible.
okay, ma'am. Okay. Let me resume my presentation. Uh, so the poly excade, as I have said you, it is you can represent by means of unitary not operation that is equal to 0, 1 on 0, and
Excuse me, ma'am. You had paused the screen
how
sharing.
the
Ma'am, screen is not sharing, ma'am, actually. Can you just check it out, ma'am?
okay, ma'am.
It's visible, ma'am, now. Yes, ma'am. Thank you, ma'am. Yes, ma'am. It's visible, ma'am. Then the network issues, ma'am, again.
Okay. 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 Network issues. Okay, log in again. I'll mute here, ma'am, and I'll go with the phone. Okay.
Sure, ma'am, sure.
Ma'am, give me. Okay. Hello?
Yeah, ma'am. Yeah, ma'am. Can you just mute the system one, ma'am? And you can just unmute if you're logging through mobile, ma'am. That would be better.
Is it okay now?
Ma'am, your voice is actually echoing, ma'am.
One sec.
Yes, ma'am.
Now? Is it okay?
Yes, ma'am. It's okay, ma'am. Now, all good. Thank you, ma'am.
Okay. Shall I continue, ma'am?
Ma'am, sure.
Okay. Okay. Uh, so this is the option how there is a flipping of input from cat one, cat zero. So we have this represent by means of the unitary not operation 0, 1 and to have to perform with why the second matrix is 1 0 because the cat 0 they represent the form of 0 1 1 0 and 1 0, so these make it in the value 0 1. So in such converted from 0 to 1 by using the giving an input 1, so the similar and you will be getting the value
Excuse me,
0.
ma'am. Again, there
This
is
is the
a.
one. And if it is cat 1, it is cat 1, it automatically there will be output of 1 0. That will be flipping. You all I said you there will be flipping of the input value. Automatically when you're providing the input as 0 1, that will be you'll be getting an output of 1 0. Next poly Y gate. So this poly Y gate.
Ma'am,
So it
excuse
will
me,
be
I'm
this
sorry
is
for
the sole
interrupting you.
responsibility this Y gate. So this will provide a phase split, that is it will be providing a rotation around Y axis by using pi radians. So I'll explain you, I'll provide a visualization based on this. So there will be a rotation against the Y axis. The Y axis that can be represented by means of the matrix representation 0 minus I 0. Okay. Now how the 0 minus there is this cat 0 is converted into y I cat 1, that is to his imaginary part. Okay, this is the operation step by step computation that is performed to convert the input cat 0 to cat 1. Okay, 0 minus I 0. So this is the matrix representation of the y value. This you have to multiply with 1 0 because 0 cat 1 is represented in the form of 1 0. Now when you are performing the multiple operation, so here you'll be getting 0 I. So that is equal to I of 0 to 1. So similar to that is I of cat 1. Okay. So now similarly y cat 1. Similarly you have to perform the same operation. So now the truth table of poly y gate is when you're providing an input 0, it will be I cat 1. And when you are providing input 1, it will be minus I cat 0. And alpha cat 0 plus alpha cat beta cat 1, that will be converted into its imaginary part. And there will be a flipping of values 1 to 0 and 0 to 1. So, but you will be adding I also here. Okay, there is an imaginary part. Next, poly zk. So the poly zk, it will be multiplies the sign, that is real part, similar to a real part. That is when you're providing in poly z gate, when you're providing 0, that will remain unchanged. Okay, I have said you before, no? So when you're providing the input 0, that will remain unchanged. The same output will be produced. Whereas when you're providing the input 1, that will be converted into minus cat 1. Okay. So for the z cat 0, z that you can represent by means of 1 0 0 minus 1 into 1 0, the state vector. After you're performing the multiplication operation, you will be getting 1 0. So this 1 0 is nothing but 0, cat 0. Similarly, z 1. Poly is that the similar way, the truth table. So here the conjugate. Okay, similar to conjugate, that is plus beta 1, that will be converted into beta 1. So here you see alpha 0 remains unchanged, and here beta 1. So here beta 1 here will be represented as minus beta 1. Here also you see 1 is converted into minus 1, 0 is converted into 0. Next is Hadamard gate. So the Hadamard gate is, I have already said you, it provides you the superposition of the two state vectors. So superposition of the two state vectors, that is represented mathematically by means of this equation, that is 1 by root 2, 1, 1, 1 minus 1. Okay, so here I have to perform the similar operation, and finally you will be getting the value. You see here, this is the value. Cat of plus. Okay, cat of plus, and for 1, you will be getting cat minus. I'll show you the truth table. Okay, so when you're giving an input 0, so that will be getting an output as plus, cat plus. Okay, so this is one new term now. So 1 by root 2 into cat 0 plus cat 1, you will be getting plus cat. Okay, similarly 1 cat, that when you're performing, you'll be getting minus cat minus. When alpha 0 plus the beta 1, that the similar way you have to perform the similar, that is what, you have to perform the step-by-step computations, and you'll be getting alpha plus cat and plus beta minus cat. Okay, so I'm not dwelling in depth into how it is performed, everything, because we have to see multiple, some other slides are there. So if you want, I'll provide you some more slides later. Okay. So because this computation, it will take some more time. So you can just remember what type of conversions will be taking place in the Hadamard gate, how the superposition is emerged, superposition is property satisfied by the qubits. Okay. Now I'll just provide you this slide. Okay. I think the slide you'll be able to view. 1 second.
Yes, ma'am.
I think you are able to view the slide. No. Okay.
Yes, ma'am, it's visible, ma'am.
So you see here, this is just a visualization how it is being performed. This is our X gate, Y gate, Z gate, Hadamard gate, S gate, and TOF. So these are here. The gates are, as I said, north 0, south 1. You see how yes. So yes, now value will be getting.
Excuse me, ma'am. Again, the
Now
network
I'm going to
interruption.
perform the edit. Okay. When I how you see how that is the point one to that is north pole to south pole and south pole to north pole. So now automatic now load spare. So here when it performing the that we can the poly that is zero value. Now I'm going to perform use now value is not zero. Now I'm going to wide. So the value is the and here you see how it is being performed. Now, so when you're in zero, Y gate, when Y gate. Now you're providing input, you see here. Around y-axis, it will be performing internally. Okay, it will be performing internally. I just show you the slit by slit. Y gate now it is in zero state. Now it is 1. I'm just going to polar angle. Now performing state. Okay.
Excuse me, ma'am. Again, the network interruption.
See how the
Your
values are
voice is
being
little bit.
changed. Okay, so this represents the real part and imaginary part. So here the 0, gate 0, and this is alpha 0, this is beta value, beta 1. So beta is nothing but the real part and imaginary part. The alpha remains a decimal value or some real value. Okay. So once again, y vector, so y gate, so y 0 is converted into 1, whereas for when converting 1 to, when you're giving input 1, it is automatically converted here, you see, 1 you are provided, alpha is 1 and 1 is of alpha beta, 1 cat 0 plus 0 cat 1. Okay, when I'm going with z axis now, it is in input 0. I'm performing now z value, it is rotating around the z axis. You see here the rotation is being performed here. You see here the rotation. How it is being performed. So automatically it is being rotated and you are getting the state vector. The qubit state is being changed. Okay. You see the qubit vector is being changed from z axis when you are performing. So it is there will be rotational basis from z and y because y will be providing you the real part and the z will be providing some imaginary part. So there will be a rotation along the x axis, sorry, y axis and z axis. Okay. And we didn't go with the Hadmat gate. Hadmat gate will be providing the superposition value. You see here. So it will be, there will be a superposition between among the gates. How it is being rotated along the z axis and y axis. Okay. Later S gate and T gate, the space gate and Holy gate, you can see later because I didn't go with the mathematical representation. I'll go back with the presentation. So next is a multiple gate, that is 2 qubit gates. The 2 qubit gate is also said to be the multiple qubit gate, and The two qubit gate, the best example is controlled NOT gate. Okay, the controlled NOT gate, how the operation is being performed. You see here. So this is the XOR gate. So the XOR gate. This is the actual gate. How you will answer when both the bits are same, you will get output as 0. You will be getting the value. But coming to the C0 representation, here there will be qubit 1 and Q1 and Q2. So Q1, the same Q1 will be represented output as a Q1, and Q2, the Q2 can be represented. How the Q2 is Q1 XOR Q2. Is it clear? So I'll still explain you C0 gate. So Q1, you are representing the means of two qubits, Q1 and Q2. So when you're manipulating the Q1 gate, that will be for the output. Whereas when you're manipulating the Q2, so the value of the Q2 will be manipulated for Q1 XOR Q2. So this is controlled NOT gate matrix representation. Unitary C0. So this is your representation of 4x4 matrix. So I have said you two qubit gates, Q1, Q2. This is okay. This 0 is Q1 and this is Q2. Okay. So 0, 0, 0, 1, 1, 0, and 1, 1. Okay. 0, 0 you can represent the single qubit, the single column vector, 1 triple, C no. So everything 1, 0 is everything. Now, how it is being represented in the form of circuit representation? C0. That is a 2 qubit state, 00. That will be 0, 0, 0, 1, 0, 1, 1, 0, 1, 1, 1, 1, 1, 0. So you see here, there is no change in the first two things. There is 0, 0, will output also will be 0, 0, 0, that also will be 0, 1. Whereas when you're going with 1, 0, here the superposition property occurs here. 1, 0, here 1, 1, 1, 1, it is 1, 0.
Ma'am, actually,
So
ma'am,
here
sorry for
in this
interrupting, ma'am. The slide is not
foundations,
actually
the
changing, ma'am.
superposition property.
Ma'am, what you are telling, actually, we are unable to see it through the slide,
See
ma'am,
here.
actually.
The first column vector, it is 0, 0. So second column is it is 0, 1. Third column vector is 1, 1. Fourth column vector is 1, 0. So here this 1 triple 0 can be represented by 0, 0, and this 0 that is represented by this second one. So these are the basic states. Okay, how the basic operations are being performed here. So this is C0 gate. C0 gate will be having two qubits. So on two qubits, the first qubit there will be a hole. Okay, there will be a hole, and in the second qubit there is a target gate. This is the input line. You can see. You can just say input line, and here you will be a output. There will be a communication or a connection between the two qubits. Okay, first qubit and second qubit. In the first qubit there is a hole. That is a round. Okay, in the second qubit there will be a XOR operation. So I have said, so we come here. Q1, there will be a hole. That is, but Q1, the same thing it is represented as target value, whereas Q2 will be the XOR. So the symbol is XOR value. XOR symbol heading here. Okay. Now, one more property of CNOT gate is one main important property of CNOT gate, that is two qubits. Okay, why two qubits? How the matrix representation is represented? There are CNOT 3. So here in CNOT 1, this first gate there is 0, 1, there is 0 XOR, and the second gate it is XOR 0, and third one there is 0 and XOR. The 0 is the sense hole. It is a small hole here. It is by means of a connector. You can see it is a connector representation. Now it is an alternate. The first gate will be having connector and an XOR. The second gate will be having XOR and a connector, and the third one will be having a connector and a XOR. Okay. I say why we are going with the qubits back and how the matrix is being represented. A, B, 0, A XOR B. Whereas when you're going with the CNOT gate, it will be A XOR B. So this is the computational formula to calculate the CNOT gate. Okay. A XOR B. First, you have to perform A XOR B, and after that, with that result, you have to perform A XOR the resultant value. So you will be getting the truth gate. Okay. Here A XOR B is 0. So you go with the first row. Now you have to perform A XOR B. So A is 0 and A XOR B is 0. So both again you are performing the XOR operation, you will be getting 0 value. Similarly, all these 3 bits. So now I have said you swapping. So swapping of two controlled NOT gate, that I have said you there will be 3 gates. Okay, 3 gates in the sense that you can represent by means of time swap. Okay, before that I have to explain why we are going with. So you will be performing NOT operation using 3 controlled NOT gates, and there will be a sequence of 3 NOT gates applied one after the other. There's sequence, there will be a time sequence. Okay, so the CNOT gate will be represented vertical line, and by using a controlled bit and a target qubit. I have said there is a connector and a XOR operation. So that connector qubit, you'll be seeing a control qubit. The first qubit is a control qubit. The second qubit is the target qubit. So I have two qubits in the control target. The first qubit and the second.
Ma'am, your voice is breaking, ma'am.
Control
Actually.
qubit. The second bit is controlled qubit by means of the target qubit, that is XOR operation, XOR sign. So now you are going to perform the controlled gate at 3 or at 4 time sequence, that is T0, T0, T1, T2 and T3. Okay. So T0 is the initial state. The initial state is Q1, Q2, Q1 comma Q2. You come here now. So at time sequence T0, a time sequence T2, a time sequence T2 and time sequence T3. Okay, at each and every time sequence. So T0 is nothing but the initial state condition. The initial state condition Q1 and Q2 will be the same, because before passing the input to the controlled NOT gate, first controlled NOT, the value of Q1 will remain. Okay, at the time sequence T1, the Q1 and Q2 must be controlled NOT gate. Result as Q1 comma Q1 XOR Q2. Okay, now so here it will be a Q1 and here it will be Q1 XOR Q2. Now you are providing at the time sequence T2, you will provide the input the same, that is the bit gate. Okay, T2. So T2, the first qubit will be Q1, the second qubit will be Q1 XOR Q2. So this is the value of the second one. So you come this one. This at this particular time sequence, timestamp T2. Okay. Now you have to perform Q1 XOR Q1 XOR Q2 and comma Q1 XOR Q2. Why we are going here? Because the same time sequence T2, it will be a connector. Okay, the connector is but controlled qubit. If it is a controlled qubit, the input remains same, and if it is a target qubit, there will be an XOR operation. At time sequence T2, the Q1 bit will remain, so it will be performing XOR operation, and at next one you'll be performing the same thing will be remaining. After the T3, the same will be happened finally at times T3, you will be getting final Q2, Q1. Here you are getting a reversible value. At T1, the value of qubit is Q1, Q2. At time T3, you will be getting Q2, Q1. So I hope you have understood this working principle. Okay, somewhat you might have understood. Okay. So after this, why we are going with the swap gate? So I said swapping, you have to perform swapping. Why we have to go with the swap? Okay, because the qubits are not at all connected to each other in the classical computer. Okay, so the location of bits will be irrelevant in the case of classical computer. That is, there are in the classical computer, you will be performing manipulations using bits, and each bits will be in any of the memory location. Okay, so the first qubit, that is memory address, will be irrelevant. That is, the first bit will be in some memory address, for example 2000, and the second bit may be in somewhere 3050, some memory address. So it will randomly spelled out. The bits will be randomly spelled out. Wherever the memory location is free, there will be, it will be uh, fixed. It will be filled, or it will be filled. Now, quantum computer, but this location is not a matter of computer. Scat frame and the manipulation of operation. As a memory, not a matter when compared to a classical computer. Whereas when you're coming to a quantum computer, the location is more important, because there comes the entanglement. Okay, there comes the entanglement, because the property of entanglement has to be achieved, the superposition has to be achieved. So the superposition and entangle could be achieved only when there is a proper location, when only the location is being what I can say, being reflected. I have said, the first person will be able to predict the answer of the second person, and the second one will be able to predict the first person. So that is the entanglement property. That entanglement property can be only achieved only when the first bit will be able to identify the location of the first, the second bit will be able to identify the location of the first bit. So, okay. So some physical memory, physical be there, and
Hello, ma'am. Hello, am I audible to you, ma'am?
in the second qubit. So that connectivity should
Ma'am,
be
actually the
available.
time.
Okay, should be known, predicted, so the entire property can be achieved. So now entire property is of gates.
Hello, am I audible to you, ma'am?
There will be
You will be alone. Sorry for interrupting, ma'am. Ma'am, the time period is actually till 9, ma'am. Actually.
Will be performed by the pumping of bits. Okay, the internet value will be handed as to the next node, and so on. This will be handed over. The value of the previous gate will be handed over to the next gate, and so on. This will be taken out. This will be taken out. So that is simply a hand operation. Okay, so that hand to perform to achieve that hand of operation, you should know the address of the qubits available, and there should be some connectivity between the qubits. Okay, so that is possible only then there's a swapping operation. Only swapping operation. Okay. So only by using the swapping operation, swapping property, entanglement could be achieved, superposition can be achieved, and when both these properties are maintained or ensured, automatically the complex algorithms and complex operations can be performed in a matter of time. Okay. So this gate multiple, this can be 5 cube or 7 cube. Okay, there is a high cube. You can just add the funds derivation part, and also there are real part. Okay, so the high state part in the first location will be 1 0 0 I. Okay, now when you are performing, when you are giving an input as 0, so that you have to perform the matrix operation, tensor operation. With 1 0, you will be getting 0, and when you are providing the input as 1, it will be provided to I1, imaginary part. this is the truth table of the phase gate. Okay, 0, automatically the same will be the output, 0 and 1 automatically, sorry, that will be converted in the form of imaginary 1. Alpha 0 plus beta 1, that will be converted into alpha 0 plus I beta 1. So take this will be seeing a Toffoli of about pi by full rotation of the sphere, it is a pi by 2 value. Pi by actually around that axis it will be performing the rotation value, and there will be a what I could say exponential rotation, exponential changes in the values. Okay, so 1 0 0 e power e to the power of I pi divided. So this similarly you have to perform the this is the table of CADZ changed and power of pi I pi get okay. So Toffoli is a 3 gate. It is a 3 qubit gate. So 3 qubit system Q1, Q2, Q3. So in Q1 there will be a controlled bit, and Q2 there will be a controlled bit, and Q3 will be having a target bit. Okay, target qubit. So when there is a controlled qubit, the input remains unchanged, and when there is a target qubit, when there is a target qubit, so there it will be performing acceleration. So here Q1 remains unchanged as Q1, Q2 remains unchanged as Q2. As when you're providing input as Q3, that Q3 will be converted into output as Q3 x Q1 Q2. Okay, Q1 into Q2. There will be perfection. This is the way the Toffoli gate will be performing its operations. This is the what I can say. This is the elaborated truth table. Q1, this is Q3, so that convert output dash Q3. So you have basic states for this is the 3 qubit system. 000, 111, 010, all the 8 combinations of the basic states. How it is being represented in the form of the vector format. Okay. So here 000, that you can say is 0 tensor product of into 0 product of 0. Then you'll be getting a bit column vector. Here 001, 0 cat 0 XR tensor product of cat 0 into tensor product of 1, so that you can convert that to 8-bit factor 8-bit 1 column vector value. So work it out. Similarly the other things also the same thing what I've explained you. So that is how transformed in the form of cubic gates. Yeah. Next, how to build a circuit. Okay, before I go to this topic, I would like to see you what's the application gates. Okay, when you're able to understand that, okay, I'll explain regarding the quantum cryptography of exchanging the secret keys. And you all know cryptography is nothing but encryption and decryption of the passwords and everything. And here you consider, wait a minute. Okay. You are performing the quantum key distribution. So you're performing the key distribution with Alice and Bob. You consider that Alice is in some location and Bob is in some other location. And here you're performing the key distribution. Okay. So in this key distribution exchange, you're performing in more secure manner. You're performing more secure the property of quantum here. Because I said you are in different locations to exchange the key, there's no indication exchanging that you have to ensure it. Okay, so you have to validate the keys after key exchange. How it's possible? Okay, so you consider the pair. Okay, it's a random value. The allies will be getting a coin. You go with the coin. You can go with coin or bit or something. You can go with a 0 bit or 1 bit or plus value or minus value. Plus or minus value will comes with the superposition value. Okay, it may be a superposition value. So here, once the key has been quantum cryptography, some algorithm, quantum algorithms, some key has been exchanged with and Bob, then they will be validating it. Okay, they'll be validating it and they'll whether that is any error in bit they have exchanged or changed the keys. Be good with some possible combinations. Okay, so here they will be having the random combinations. So this first second column and the third column that represents the allies value, and the second column, fourth column and the fifth column, they represents the Bob calculation. And finally, when both the values gets matched, you can say there is no hacking. If the basis does not get matched, you can say there is some hacking. So here validating the procedure. Here you consider that Alice has get the the bit 0, and Bob has a 0 quit. So when only the validation procedure is performed in both the sides, Alice and Bob, and they has to give the same value. You might have known about the digital signature, right? The digital signature, both signatures has to be same. Only then you can come to a conclusion that the keys are same. Okay, now here the value of the digital, there is a validation value is 0. Here also Bob would validation value is to 0. So when both these values are 0, after validation, you can come to a conclusion that there is a match existing between Ali's value and Bob value. So then you can come to a conclusion that when there is a perfect match between Alice and Bob, you can come to a conclusion there is no hacking taken place. Okay. And next one, when there is a misplace or when there is a different value between Bob and allies, that particular bit will be dropped by both the allies side and also Bob side. So whenever they are getting bit values one by one from exchanging the bit values between allies and Bob, they will be validating each and every bit. Okay, they are when they're validating each and every bit, only when the match only when the match exists, they comes to a conclusion that there is no hacking taken place and that bit will be taken into consideration. Okay, when there is no match between the allies and Bob, that particular bit they'll be coming to a conclusion that there might be some hacking taking place. Automatically that particular bit is dropped down by both the parties. Okay, so here plus minus minus match taking place. Superposition also. This plus minus represents superposition. The 0 1 represents the normal values. Okay, so also when the superposition validation is also value is also same, there will be a match exist. Only when the match exists, that that bit will be considered for key exchange process or for the cryptographical process. Otherwise, it will be left on. So this is one application where quantum computing is performed. Now I'll go with a simple circuit diagram. So this is a simple circuit diagram. So here qubit here at a qubit state. First qubit gate, but input the 0 0. In the first qubit gate, is state that you are performing a superposition. So there automatically perform a superposition, and that superposition has to be entered the control cube. Okay, it will be entangled, performing the superposition. So the value gets remain unchanged, and after that the output will be taken off. Similarly, the second qubit position, what is the value is 0 or 1. So that we are performing the XOR operation, and will be passing into the XOR poly, then the output will be taken off. Okay. So finally be 0 cat 01 plus cat 10 divided by root 2. So now this qubit 0, that will be the Alice qubit, and the qubit second qubit 0 will be the Bob qubit. Okay, so now these are the two values which they got. That is, when there is a 2 qubit application which is using a 2 qubit, the first state will be and the second qubit state will be available with the bomb automatically. So means the first qubit gate is nothing but one operation performed by Alice. The second qubit state is nothing but represents the second operation performed by bomb. So both are performing the same time. We're performing the same time. So automatically both the values entangled. The output of all the both the values will be entangled, and you will be getting a common output or a common result. That will only mean in a quantum amount. Okay. So what's the what is in this particular state?
Salvi ma'am,
In this
sorry for the
particular,
interruption. Hello, Salvi ma'am. Sorry for the interruption. Voice is not
I
audible properly.
might have got something quantum computers. Other than some audible issues, what we have faced, I think you yield some gates and circuit models, so that you can take that further into some applications. Okay. I like to complete the presentation for the opportunity provided by Sridevi Institute of Engineering and Technology. If there is any queries, you participants can raise me. Yeah, I'll share the PPT. I'll share the PPT.
If any participants are having any doubts, you can just clarify it now. You can just unmute and you can just ask.
Any queries?
Dear participants,
So all are in the rush up to have their dinner, right?
actually it's 9:15 by right, ma'am. Actually, the session was wind up at 9 o'clock.
9 o'clock.
Now it is 9:15. No worries, ma'am. The participants, do you have any queries? Please kindly ask to ma'am, or else you can put a queries in the chat box.
I hope no one is having any kind of queries actually, even though there was interrupts in the network issues, but the session was really good, ma'am. Thank you so much, ma'am, for sharing this the knowledge. So on behalf of our
Okay,
institution,
ma'am. Okay,
it's my
okay.
privilege, ma'am, to deliver the thank you, ma'am, and I extend our heartfelt gratitude to our esteemed resource person, Dr. Selvi ma'am. So for sharing your knowledge, valuable knowledge and the time here, ma'am. So thank you so much, ma'am. And I request everyone, the participants, to fill the feedback, and it has been shared already in the chat box, and even the attendance too. kindly fill it out so that you can come and log in tomorrow at the same time. This session for 5th session in the day 3 tomorrow at 6 p.m. So thank you so much, ma'am, Sylvie ma'am, for sharing your.
Thank you, ma'am. Thank you. Thank you.
Thank you so much, ma'am. And everyone kindly fill out. So just the feedback and the attendance. So we can just wind up this session, the session for
Yeah, with this
today.
note, I
So
too will leave the sessions.
yeah, ma'am. And we'll meet everyone tomorrow at the same time at 6 p.m. So kindly log in at the same time. Yeah, sure, sir. We'll make sure that we'll share the PPT in the groups. And thank you so much for all the participants. Thank you so much, ma'am.